𝖘𝖔𝖈𝖎𝖆𝖑𝖘. 𝖘𝖔𝖈𝖎𝖆𝖑𝖘. What's poppin', gamers? It's your math gamer over here, alephmuvt, coming in live on a beautiful Monday morning. We're gonna be doing some more math reviews. You know, it's like inspection day, except you got to make sure that people have made the right thing. Also, we hit our 200 follower goal. We hit that offline after last stream. It was, hold on, let me also mute some stuff real quick. No, that's right. Yeah. No, we're good. Yeah, we hit our follower goal yesterday. During a raid, we had 𝖘𝖔𝖈𝖎𝖑𝖘 come by and drop in with like, oh my goodness, like almost like 200 viewers. It was amazing. So she came in and, you know, was wanting to support us. She's like a physicist, a PhD physicist, and does a lot of like individual work and stuff. So if you ever check her out, I'm gonna pull up her Twitch, but she seems to have been around here for a good minute. So if you check her out, she came in and raided us yesterday and then helped us hit our follower goal. Insane. And also yesterday sucked because the, what do you call it, we had the worst lag, the worst possible scenario for everything, and it was embarrassing. It was incredibly embarrassing. So but she came by and that was cool. Yeah, she came by. It was actually amazing. She was invited to do these reviews with us. Unfortunately, she's busy, but she came to support us in different ways. So crazy, right? Crazy. So shout outs to her. Maybe we'll go back and commit a raid of our own while she's live one day. But now she's on my radar. I had no idea who she was until she came by yesterday. Insane. Anyways, all that to say, we're gonna do more math reviews. Waiting for 𝖘𝖔𝖈𝖎𝖆𝖑𝖘 to finish up. In the meantime, how's it going? How's everyone doing? I see we have 𝖘𝖔𝖈𝖎𝖆𝖑𝖘, we have Aleph, we have Terry. Hi Terry. Terrified Games. Go check out Terrified Games on twitch.tv/Terrified Games. We have 𝖘𝖔𝖈𝖎𝖑𝖘. Hi 𝖘𝖕. Hi Aleph. With all the new emotes that I love. They're so good. Hi Terry. Hi 𝖘𝖕. Hi 𝖘𝖕. Imagine doing math on a number line. It's on the number line. It's all just 2D math. That's what we're doing. 1D math. One math. Just one. Not even specifying. One apple, one orange, just one. I don't think I made my announcement yet, so I'm gonna have to make my announcement real quick. Check me out on YouTube as well. It helps me get those watch hours as well. So I can hit, what do you call it? So I can get monetized there faster. Surprisingly, live streams on YouTube do help you with that a lot. It's crazy. So I hear. I believe probably 𝖘𝖌𝖎 hit those hours like a long time ago, so he's probably getting monetized now, even if it's not a lot. And then I think my friend 𝖘𝖌𝖎, she's also on there too. Try to watch on the YouTube. Try to watch. I mean, I will do like YouTube only streams for a minute at some point. Take your time. Today's gonna be a long stream, so we're gonna go for like 4 hours today. But yeah, YouTube at some point I'm gonna have to like. I want to rush YouTube and get that crunching. So yeah, that'll be fun. Let me make my announcement real quick and then let me see. Let me go ahead and make an announcement real quick and then see what everyone's doing. So everyone, we're live with more math reviews. Oh, you might have noticed as well, we don't have 𝖘𝖌𝖎. Unfortunately, 𝖘𝖌𝖎 couldn't make it today. Bummer. But it happens. It happens that way. He's got a lot of stuff going around the house, so it is what it is, and I hope it won't. So it is fine. Where do we do 0D math points on that direction? Well, that is gonna be coming up in, I think, baby math. That is like, so actually zero-dimensional math is very uninteresting, like just as a whole, but there's a remarkable thing about it, quote unquote remarkable. So because of how I think I like, you guys probably know this already. I like 2D math. I like 3D math. 3D math a lot. I want to try getting into 4-dimensional math. There's this book I have called Computational Physics. I'm sorry, Computational Geometry. I got that from a friend, and it was actually really cool. Let me see if I can pull it up and break TOS or whatever the case is, but it's a pretty cool resource. Ah, okay, there it is. Hi, Stooky. That must be Stooky, right? Hi, Stooky. We are about to get started. I'm just sharing something really quickly about a book that I have. Let me move over and share what the book is real quick. How was your reviews? How was it? How do they all go? How do they all go? I'm about to get started with some of that, but I just want to say I'm gonna look into some of this math real quick from this textbook. This is called Discrete and Computational Geometry. I think this is like a resource a friend of mine gave me. So, and it covers a bunch of stuff that I do already in 3D stuff. Rat raid, rat raid, rat raid, rat raid, rat raid, rat raid, and run. You dipping? But this is like your typical kind of computational stuff. And it also covers those theorems like the fold and cut theorem and I think some like the origami stuff as well. So this is a pretty interesting resource. I'm going to research this on my own time. Thank you for the follow. Is that Cell Stuff? Is that your name? Let me take a quick look. Sorry. Say Stuff. Hi, Say Stuff. We're gonna get started with SoME real quick. Sorry, I just wanted to share like something early before we get started. So, yeah. Since it's just gonna be me today, and I found out that watching videos could suck for me, it's gonna be a lot lighter on my end. So. Notice me on YouTube. Sorry. In that case, I'm gonna move over to the other screen because as clean as this screen is, I had the YouTube chat on the other one. So yeah, this is a book that I got. This is called Discrete and Computational Geometry. It's just a field that I'm interested in because I do a lot of 3D math already, and I figured I may as well actually learn more about the fundamentals because I understand the graphics side, how it operates, but I want to learn more about like some of these lemmas, some of these theorems and stuff, right? Like that Euler one about like how many sides a polything has, a polyhedra has. Oh, this is like one of them. I've seen this one before. 5 polygons, all mapped to the same polygon under a contraction. Yeah, so theorems about like triangulations and stuff like that. That's kind of cool. Triangulations. Yeah, this is just a resource a friend shared me, and I wanted to get into that at some point. Why did the mathematicians rent a motel room? Why? And I see you coming. Hello. I see you on YouTube. Let me move over to the full screen to do discrete math. For sure. So let me move screens over real quick. Nice lag. Healthy. I believe I'm on the corner over here now. So yeah, now I have YouTube chat and I can see you both at the same time. So I can actually do both. So, I wanted to get into some of we'll do some videos today, as well as some of the non-video submissions, because I feel like they need some attention and love as well. And we'll want to cover them as well, because, I mean, they need some grading. So, and that's a lot lighter on my side as well. So, let us try getting to some of this. We have the choice between the video, which is why is root 7 missing on these cubes? I have a picture of this particular one as well. If I have media to share, hold on, where is it? There's a meme that I have seen this before, and I actually made an animation kind of it, covering that specific subject, but I didn't actually get far in it. Maybe I could share that real quick. But I was covering this as well. So that's like a quick graphic from the thing I covered. So yeah, I'm slightly familiar with the root 7-bit. I don't know how to prove it, and I don't think it was proven until like a long time later. So, Aleph Senpai Daisuki. Grateful for witnessing good sources of knowledge. Yeah, I'm not the best for that. I'll be honest. But I will appreciate. You guys are along for the ride, so we're here to hang out, do some math. We have a big session today. Oh my gosh, like 4 hours, right? So I have some bagels with me, and I have some coffee with me. And if I need to take a break, then I have even more coffee, and might be able to eat. But I want to get started with the non-video submission, just so we can get that going. So yeah, if you have any, you guys get bored or have any interactions and stuff like that, you can use the redeems and stuff. They're fun. So yeah, go ahead and use them, and if you're a subscriber, you can use the funny emotes. Okay, let's get started. So this one's called Making Your Neural Networks Even Smarter. High school and undergraduate level, deep learning, differential equations, scientific machine learning. What happens when you give our neural network more than just data? Through this article, we try to explore something called physics-informed neural networks, which can help us solve differential equations. Oh boy, differential equations. My favorite subject. I'm not the best with them, that's why I say that. We define the architecture and build one to solve a 1D heat equation. Oh my gosh. We also dive into the math on how PINNs work, where they work well and where they don't. Okay. Let's go ahead and check this out. I'm also just gonna crop. I forgot I don't have my tabs cropped, but I like to crop my. There you go. So you can't see my tabs. So let's check out this one. This is called The Rabbit Hole. Like Funny Bunny? This is not Funny Bunny. Not Funny Bunny worthy. Making your neural networks even smarter. Who doesn't love good neural networks? Okay, that's a very biased question, but I should probably be targeting the very niche audience with it. Since you're reading this, I'm going to assume that at least you're somewhat interested in neural networks. I kind of am indifferent to them. I thought they were pretty cool. I remember when they were striving for that during computer science and really making it a big deal, and then AI took over. So kind of this math and stuff, it's not obsolete, but the stuff that was relevant is completely like irrelevant now. So, but the scales and neural networks probably better for like video games and stuff, and some very like light work cases, as opposed to like AI being shoved into everything right now. So I kind of don't mind. They're cool. Neural networks have become remarkably good at learning patterns from data. Give them enough examples, enough compute, and a sufficiently expressive architecture, and they can learn functions that would be extremely difficult to write down explicitly. But there is an interesting questions hiding underneath all this. What if we already know something about the function we're trying to learn? That would be incredibly helpful. What if we know that a solution must satisfy a differential equation, but we don't have much data describing the solution itself? Instead of asking a neural network to learn everything from data, perhaps we can teach it some of the rules of the world. That is the basic idea behind physics-informed neural networks, or PINNs. Okay? In this article, we're going to build one from scratch and walk through how it works. Instead of starting with a complicated partial differential equation, we're going to start with a much simpler system, a hot metal rod. The goal of this article is exploring what PINNs are and how they work. This isn't an intro to neural networks or solving partial differential equations. Wherever applicable, I will provide links and external sources so that you can read and catch up with the content in this article. Okay, I appreciate that. That's pretty cool. So, we're going to be learning about how these work. Forgive me. And we're not exactly getting into the nitty-gritty. Well, okay. I can see how long this is. This is quite extensive. So I probably will give myself a time limit to get through this. So I want to say, let's give ourselves like 20 minutes to get through this. So right now it's currently 11:10, 11:20. So I want to say around 11:40 to get through this. Because I can probably pick up on the math and then intuit a few things, but I don't want to be rude and just get through this as fast as possible. Sound good? So then they submitted an essay. It looks pretty extensive. This is about how PINNs work. So at face value, it looks like a lot. How short should articles have been? Because this looks like a full research paper. Not like a research paper, but it's pretty extensive. That's what an article should be, though, right? It's at least getting through all the bits with visuals and things and interactive stuff. So I can dig this for a second. And honestly, looking through it, I don't think it's actually that much. Just reading through everything. So yeah, we'll give this one a shot. So 20 minutes on the clock right now. Okay. It's Aleph. Hi, Tyler. We're learning about PINNs, physics-informed neural networks. How does a neural network learn? Suppose I give a neural network some inputs x and ask it to predict an output y. We can write it as y hat as a function of theta of x, y theta, where theta represents a neural network and theta represents all of its trainable parameters that would be weights and biases of the neural network. Okay, so you put in that thing in, and you're gonna have a bunch of like parameters read through that thing, which may be variable. For example, if you with mean squared error, statistics, L is equal to this equation, the network changes its parameters to make its loss smaller. The basic recipe is input goes to the neural network, which goes to the prediction, compare with data, and then you update. Oh, okay, so you're actually comparing it as opposed to just spitting out stuff and then constantly going back and guessing to find the win condition. This works extremely well when we have lots of good data, but scientific problems often don't look like that. You could read more about neural networks here, neural networks. Okay. Also, if you want to read this article as well, I'm going to pin this in the chat as well. I'm going to leave that up for exactly that 20 minutes, and once it's gone, then it's going to be gone. All right? I'm a raider. Oh yeah, I was pulled up on your chat. That's funny. All right. Oops, data is expensive. Imagine that instead of classifying cats and dogs, we're trying to predict the temperature inside of a piece of metal. We could measure the temperature at many different positions and times. For example, we might know that we have these values, B42, then this value is at 68.7, and then okay, yeah, basically we just changed the parameters. Different location and different time. We could give many such examples to a neural network and ask it to learn about U of x and t. Getting enough measurements to describe the temperature everywhere in the rod would be expensive. We also don't have to rely on measurements alone. We already know the rule that governs how heat works through a rod, the heat equation. This gives us another way to judge the network. Its predictions shouldn't just match the temperatures we measured. We should also satisfy the underlying equation. So let's heat up a metal rod. Consider a one-dimensional rod. Its length would be 1. Okay. And let this represent position and time. Suppose that a rod starts at the temperature distribution shaped like U of x, 0 as a sine value. Why sine? Because it starts at 0. So the center of the rod starts hot while the ends start at 0. Okay. We hold both rods together at 0 temperature. They will be 0 and 0. How does the temperature change over time? Good question. We have the heat equation. The answer is governed in one-dimensional heat equation, known as this. Partial is equal to the alpha double partial with respect to U and X. Here, alpha is the thermal diffusivity of the material. For example, we'll use alpha equal to 0.1. If you've ever encountered partial differential equations before, this equation might look intimidating, but it's pretty easy if you have an intuition of what derivatives are. Yeah, this is relatively simple at the moment, at least. What are derivatives and how are they helpful? Before worrying about partial differential equations, let's remember what an ordinary derivative means. So we have a function y of f of x. Its derivative is how quickly y changes when x changes. If the derivative large, the function is changing rapidly, and if it's 0, the function is locally flat, of course. Now imagine that our function depends on two variables, x and t, and the notation partial u and partial t. So this is just covering how partials work, which I already know this part, but I kind of like how this is like breaking it up. It's like, instead of doing it all at once, which can get complicated, you can just separate one of the variables and treat the others as constants. So I wonder if it says that. These partial derivatives, like our function, depends on multiple independent variables, like our function u here, which depends on both x and t. Using partial derivatives, we can look at how our function changes with respect to one variable while keeping the others fixed. Yeah. Similarly, partial u, partial x tells us the temperature change along as we move along the rod. And partial u, partial x squared tells us that the spatial rate of the change itself is changing. So yes, simply means that it describes the curvature of the temperature profile along the rod. If you think of it, the heat equation is telling us something quite intuitive. The way temperature changes over time is related to the curvature of the temperature profile in space. A highly curved temperature profile tends to flatten out as heat diffuses, and that's exactly what we expect to see physically. So, I don't know if it should be introducing the word curvature just yet, because maybe with some graphs it would explain how a big curvature influences like the rate, and then how a low curvature affects the rate. But that is the proper word, because when you have these different rates and relations, curvature tells you basically how fast it's going, or its rate of change, the rate of change of rate of change. So yeah, that's I'm okay with that. Nothing here sounds bad at all. I think this is fine. What does the solution look like? For our particular initial and boundary conditions, the exact analytical solution happens to be all of that. At t equals 0, this reduces to our original condition, u of x comma 0 is equal to sine pi of x. As time increases, the exponential term gets smaller, so that term approaches 0. So the temperature profile gradually decays towards 0. That gives us a pretty nice starter problem to implement the PINN. We're not even there yet. We know the answer, but we're going to pretend that we don't. I wonder why we would use PINNs then, because when we know what the answer should be, is it supposed to be the equation itself, or is it just the method, the actual numerical solutions that we're supposed to get, right? Because I know in some sims that I've done that you do have your boundary conditions and you do know what you're trying to approach, but we don't know everything about it, or what's the best path and stuff. Kind of like that 𝖘𝖔𝖈𝖎𝖊𝖉𝖎𝖙𝖘 video that we watched last time. That was pretty cool. I'm having a bite of my bagel now. Forgive me. I have one with salmon, and then another one with ham. And I cut some onions with it too. It's pretty good. Okay. Alright, forgive me. So, yay, it's time to define our neural network. Let's replace the unknown mathematical function u of x of t with a neural network. Our network takes two numbers, x and t, and produces one number, the prediction, u hat of x comma t. Okay, so hat must mean the neural network influence. There it is. At the beginning of training, the network has not learned the temperature distribution yet, so its predictions will be far from the actual solution. However, since the network is differentiable, we can use automatic differentiation to calculate derivatives of its output with respect to its inputs. Okay? Explode. We can calculate the partial of the neural network and the rate of change of the rate of change, where the automatic differentiation becomes extremely useful. What's that? Automatic differentiation. And then it takes us to an article about automatic differentiation, also called autodiffs or ADs. That's kind of cool. So that's a nice way to plug in your resources, your sources. I like that. That's really nice. Using the physics for the loss function. Remember our heat equation? If our neural network were producing a perfect solution, then plugging its prediction into the equation should give us 0. So let's define the physics residual as the residual of our parameters is equal to the difference of these two neural network values. The closer r of x of t, x comma t is to 0, then our prediction satisfies the heat equation. Yeah, because we don't want to be off. And therefore define a physics loss as 1 over n, the sum O over Rn of all these residuals squared. Kind of like a statistics thing, I wouldn't know. Now that the neural network is being punished, well, whenever it violates the physics, this is the fundamental idea behind the PINN. It's getting punished when it violates the physics. I like that phrasing. Completing the physics, we're only still like halfway, so that's still a good ways away. I'll read it a little faster. We're not done yet. We got a small, teeny tiny, or not problem. Suppose that you find a function that satisfies this. Oh, okay. U of comma x, u sub xx. There isn't necessarily one function that does that. We need to tell it the network about the conditions of our particular problem. Boundary conditions are this and this. So we create a boundary condition loss. Ooh. Where MSE is equal to uses these parameters at 0. So between the rod, this is the rod at 0 and rod at 1. So both ends of it. We have our initial condition, u of x comma 0 at sine x. So we create another loss where we need to match MSE. I wonder what that stands for. Okay, of those parameters. Our network now has 3 responsibilities. It's such a hard worker. It needs to satisfy the heat equation, satisfy the initial condition, and satisfy the boundary conditions. I'm on board with that. We combine them, L physics plus IC plus BC. Okay, that's essentially our PINN. So we also have this. I'm a little confused on what this means though. Boundary condition loss. So I'm okay with that. Initial condition, boundary condition. Whatever you say, Stan, I will accept what that says. What makes it physics informed? A normal neural network might learn that x comma t approaches u by looking at the examples of temperatures. Is that obtuse babu? Thank you for the follow. I appreciate it. We're covering math. This one's about neural networks. Our PINN instead learns by minimizing the combination of constraints. It is effectively being told, I don't necessarily know the answer at every point, but I know what rules your answer must obey. Okay. The network therefore learns a function that simultaneously satisfies the data conditions and the governing differential equation, or just the governing differential equation if you don't know the data, if you don't provide it any data. This approach was formalized in the modern PINN framework by Racy, Paradikaris, and 𝖘𝖔𝖈𝖎𝖙𝖘, who demonstrated by using this I can't read. Who demonstrated its use for solving forward and inverse problems involving nonlinear PDEs. That's cool. Okay, so we can use this thing to solve stuff. We can actually do that. Where do we evaluate the physics? Our PDE applies through the entire domain. So we have the 2 parameters of 0 to 1 and then also 0 to 1. But there are infinitely many points in that domain. We obviously can't evaluate the residual at every point, at every possible point. Instead, we randomly or systematically choose a collection of points inside the domain. These are called the collocation points. Collocation points. Let me also zoom in a bit more. Collocation points, sure. For example, if we have these points up to n, at these points we calculate the residuals. We minimize the average squared residual. This is one of the reasons PINNs are attractive. The neural network operates as a continuous function over the domain rather than requiring the traditional mesh to represent the solution. That's why. Okay. So we're operating the function over the domain instead of a mesh. Because I know in simulations, you generate a mesh and then you can evaluate values between your squares. And in stuff like fluid dynamics, then you have your like Reynolds numbers. And if you have your Reynolds numbers either too low or too high, then you end up breaking this what do you call it? you end up breaking the simulation. Either your cells don't have any action going on because the Reynolds number is too small, or you're jumping data but from cell to cell, like many cells at a time, which means that you're losing data. It should be going from cell to cell between your time steps, or at least continuously, so you can see how the values change. And that requires a mesh, and that means breaking things up in a different way. In this case, neural networks operates as a continuous function over the domain. That's good. I like that. I can see the value in that now. That's cool. What does training actually look like? At the beginning of the the network produces a poor approximation. Its prediction might look nothing like the true temperature distribution. Then we calculate the physics, the initial conditions, and the boundary conditions, those losses, and then combine them. The back propagation, what's back propagation? I don't know. That's another link. It doesn't seem to work. Thank goodness, because I would not, or that's a risk. It'll take me somewhere, so I wonder what that's about. Updates the neural network parameters. The process repeats. So T is, you differentiate it, you calculate the physics residual, calculate the loss, back propagate, and then you update. Okay? Eventually, we hope the network settles on a function that satisfies all three constraints reasonably well. So now let's try out a PINN. Or I guess I'll just call it a pin now, because that's what it is. Now we can move forward from talking about it theoretically and actually implementing it. See, I appreciate that. So this entire bit wasn't too crazy, and now we say, since this is basic enough, we can totally cover this. Cool. I implemented a heat equation pin in Python using PyTorch with a corresponding MATLAB equivalent. The complete implementation is found here at this site. So that is their GitHub. I'm going to click that. That is their GitHub. Very cool. And then it has their sources. Very, very nice. I like it. The network takes x and t as inputs and predicts u of xt. Automatic differentiation is used to calculate the derivatives required by the PDE residual. The analytical solution is kept completely separate from training and is only used in equivalent to evaluate the result afterward. The exact solution. Before looking at the neural network, let's look at what the actual solution should be. The analytical solution, trust me, or don't, for the 1D equation is this. The resulting temperature field looks like this. Fascinating. So yeah, the ends are going to be zeros, at the middle it's going to be a value, and then it's supposed to be distributed in some form or matter. So only at this end of the rod, right? So at t equals 0, the temperature is highest at the center of the rod and falls to 0 on both ends. Okay, basically we got that. What did the pin predict? As we asked the neural network to produce the same solution, here is the temperature field predicted by our pin. It looks fundamentally the same, which is good, right? We want this to be the exact same, so of course it would be. Visually, the pin prediction is quite close to the analytical solution. A visual comparison alone, however, doesn't tell us how accurate the prediction actually is. Okay, we can compare the two solutions directly at several points in time and see how closely the pin follows the analytical result. So now, here is the comparison. The direct comparison between the pin prediction and the analytical solution at several points in time are this. So the pin looks like orange here, and then the exact one is this blue. And it looks exactly on the same path. That's exactly right. They closely overlap. Yay. The important thing here isn't that the neural network managed to approximate a sine function. An interesting part, though, is how it arrived at that approximation. Think about how it did it. I don't know. Sine is weird in this scenario, but I mean, I've done boundary condition stuff before. I can guess why. We didn't train it against the analytical solution. Instead, we gave it the differential equation and the conditions that define the physical problem. The solution emerged from satisfying those constraints. How cool is that? But how wrong is it? Okay. Oh, so this is our errors. Our exact value is going to be this function. So u before the neural network, exact of x and t. So when we subtract that from the original, we would get this difference here. Everything that's black is basically on point, except for some reason this middle bit right there, and then this top right corner. That's really, really weird. I wonder why the top right corner is messed up. Ideally, the entire plot would be 0. In practice, it isn't. And here's how we see that error over the field is very little, in the order of 10 to the minus 3. I mean, that's still fine, but I'm curious about why this one is so high. The pin is an approximation, and the error depends on things such as a neural architecture, arc training procedure, number and placement of collocation points, and how different loss terms are balanced. So did the network actually learn? We can look at what happened during training. The loss is the quantity the optimizer is trying to minimize. So we have this training data. The total is on the top, physics, initial, and boundaries on the different all over the place. So upon several iterations, they're still kind of close. And then later on, we get the physics and the total to be really close to each other. But then we have our initial fairly far off, and then our boundary also fairly far off. Well, relatively far off from these ones, in the order of 10 to in orders of 10. So that's interesting. I wonder why that breaks. Ideally, the loss decreases as training progresses, but our total loss is made up of several different objectives. So the physics, the initial condition, and the boundary condition. So a decreasing total loss doesn't automatically mean that every constraint is being satisfied equally well. I gotta hydrate. I will. As soon as I finish this paragraph. So decreasing total loss doesn't automatically mean that every constraint is being satisfied equally well. In more complicated pins, balancing the different objectives can become a significant challenge. For this simple example, however, the training process is enough to produce a good approximation of the analytical solution. So I'm curious as to how well this operates versus a brute force calculated approach. Is this generic in many different terms? Clearly we can change the boundary conditions and it'll automatically figure it out. Doing iterations means it's going to be using time. So finding a solution where we don't have the exact solution would be good. Even if it's a few orders of magnitude off. So let me drink my water. Oh wow, it's been 20 minutes already. I just realized. Let me finish the rest of this pretty quickly, but this is I'm kind of digging this. I'm really digging this. This one's kind of cool. And I get to practice my reading. Pretty good so far. I really like this. Okay. Also, if you're curious, I have coffee. I usually like drinking it black, but for streams, I like having it with cream and sugar. This time I have almond milk. Very yum. So, are pins better than normal neural networks? Pins are not simply better neural networks, contrary to what the title may have led you to believe. Sorry. Aw, man. They solve a different problem. They have a million high-quality measurements of temperature. Training a conventional supervised model might make perfect sense. Suppose I have a handful of measurements and I know the governing of physics. Now I have to combine the information I have, the data, and the physics, instead of relying on the data alone. Yeah, that's what I would imagine people would be doing. They're just using the physics as well, which gives people a job instead of just running all the data and then having a bunch of data analysts crunch the data. So we can actually use the physics. Crazy. This is one of the reasons physics-informed learning is particularly interesting for scientific problems, where obtaining large labeled data sets can be difficult or expensive. The broader physics-informed machine learning literature explores exactly this combination of mathematical models and data. Note, here in our pin, we did something called a data-free pin. We did not provide the pin with any data points and simply asked it to learn a function that satisfies our PDE, boundary conditions and initial conditions, simultaneously. How can we provide a pin some data and add a data loss term? We already know what the analytical solution of our PDE is. Will that help us? Would the data violate the physics? I would hope not. If you have data violating physics, then that is bad data. Or you have stuff that needs real-world examples, and in which case, that's kind of like some models, to be fair. Like if you look at space and that kind of data, the way they get some of their solutions is by approximating a lot of like things. So you can curve a lot of like of stuff. So you say like, oh, this term, this star, it looks like it's using a logarithmic term or whatever. But we can hand wave it and say, we'll just, it's in the order of like 5,000 or something like that. So you change like a function of n or something into like a constant. And that's what some models would do just to get solutions, which is weird because like that's not an exact solution. Why not just keep the solutions? And that's because of computation. Because people don't like doing math apparently when they do science. So that depends on what you use it for. Or maybe it's really valuable data. I don't know, maybe. Hi 𝖘𝖈𝖎𝖆𝖑𝖘. But yeah, this is kind of interesting. I'm digging this so far. Can pins also solve inverse problems? Ooh. So far we have solved a very forward problem. We knew the PDE, initial conditions, boundary, and the thermal diffusivity alpha. And we want to find U of xt. We can also flip the problem around. So suppose we don't know alpha and we're trying to learn this parameter. Ooh, so this would be like useful for like CAD or your engineering solutions. We measure temperature at a few points and ask, can we use those measurements and the heat equation to figure out the material's thermal diffusivity? That's exactly what you do, right? For an inverse problem, we can also treat the physics parameter as unknown. Instead of fixing alpha equal to 0.1, alpha can be a trainable parameter and provide the neural network a small amount of observed temperature data. During training, the model learns both the temperature field and the value alpha that best satisfies the governing equation and available observations. This allows a pin to not only solve a known physical system, but also infer properties that the system of that system from data. Okay, that sounds pretty cool. But they aren't magic, no, it's math. They're very easy to finish this blog here. Let's say neural networks can solve differential equations. Yay. However, that is very misleading. Bum, bum, bum. Pins have some very real limitations. One is the loss balancing. So we define the losses as the physics plus the initial conditions and boundary conditions. Excuse me. What if the physics loss is much larger than the boundary condition loss? Okay. The optimizer might focus heavily on satisfying the PDE while doing a poor job satisfying the boundary conditions. A more general formulation introduces weights. So you have these lambdas as weights. Choosing these weights can be surprisingly important. Can we have a neural network to learn these weights as well? In the impact loss, there's a link right there. Training can be difficult. Pins are still neural networks. They are optimized using gradient-based methods, and the resulting optimization problem can be difficult. A function may satisfy a PDE perfectly in theory, but doesn't mean gradient descent will easily find it. There is an active body of research studying why pins can fail to train and how their optimization behavior can be improved. Okay. Higher order derivatives aren't free. Our heat equation is required U of t and U sub xx. More complicated PDEs can require many higher order mixed derivatives. Automatic differentiation makes these derivatives convenient to calculate, but calculating them still requires computational resources. I understand that bit. Pins can't replace numerical methods. Okay. So, our simple heat equation, a traditional numerical method, such as finite differences, can solve the problem very efficiently. So if someone asks you, should I train a pin to solve this simple heat equation? The answer is you probably shouldn't. We use the 1D heat equation example here since it's easy to work with for the model a pin for. A pin becomes interesting when its ability to combine physics, sparse observation, unknown parameters, and machine learning gives us some things that a straightforward numerical solver doesn't. Pins are better viewed as another tool in the scientific computing toolbox rather than a universal replacement for traditional PDE solvers. It is a tool. It is a tool. It is there at our disposal as a potential solution. Okay? So what do we actually do? That's a cartload of content. Let's recap everything we have so far. We have a neural network. Instead of trading it solely from examples, we automatically differentiate it. Does the differentiation satisfy the differential equation? Does the network satisfy it? We construct the residuals. We minimize the losses. The central idea of the physics-informed neural network. The neural network doesn't actually understand the physics in a way the person would. Instead, we incorporate our knowledge in the physical system and directly into the training process by including the governing equations and constraints in the loss function. The network is then optimized to find a solution that satisfies those physical requirements. Also, we have an ad in 30 seconds. I will delay that. The big picture is that we have the real example. Yeah, so basically we have the same kind of thing. Neural network, differential equation, constraints. Neural network gives a flexibility to represent the unknown solution u of xt. The differential equation constraints that solution to follow the underlying physics, while the initial and boundary conditions determine a specific solution that we are looking for. The loss function combines these requirements into the simple objective that networks can optimize. That combination of neural network with physical constraints is the core idea behind pins. The code for implementing that was done using these Python implementation. Okay, blah blah blah. You change the number of collocation points, the network size, activation function, optimizer, and loss weights. You can see how the behavior of the pin changes. And yeah, so I would say that was 30 minutes of reading. They should really put like a, well, I suppose I've read that fairly fast. I'd say that was a very good read. So basically we have these different kinds of neural networks that are parameters based and has physics we need to like adjust to, instead of the other ones where it's brute forcing these solutions and then saying, is this the best one, is this the best one, you keep iterating, is this the best one, is this the best one. So I can appreciate this a lot, because this is like something I would want to use, right? Because we understand what the physics is supposed to do, and you could even use this for like, well, I like games, so I would say for game design, but maybe not that. But maybe for things like, if you have, you can use this as a solver. You can use this as one of your solvers in like your CAD programs. You got to specify your conditions, and you need to know what, I don't know, the flexibility of an object is, right? Or the stress tensors or something like that. Maybe you can use those to find out those values. So that was pretty good. I like this. This is one of many different kinds of neural networks. And this one is a very interesting one. So it's not just based on data, it's based on physics as well. So I would say that was, I would say pretty outstanding. That was pretty good. So I would say very informative. How would I phrase all this? I really learned a lot from that. That was really cool. And the math isn't the craziest thing. So this was a very informative. Would I have any gripes with this? No. They cite their sources, they explain what we do, why it's valuable. Maybe another example of like a solution it could try to do, and it's pretty good. But reading this straightforward, I think this was fairly nice. But I mean, I have the reading comprehension of like a third grader, so for me to actually read one thing makes me feel very proud. So I would say this was pretty good. That was very informative. And a pleasant read. I learned the article. I don't know. How would you guys rate this? How would you guys understand this to be? Like, if you found this as a blog, like, I can see like the sources that it gives. If I wanted to follow up with anything, then I can look into them myself. And the math wasn't too difficult. It wasn't the craziest thing in the world. They explained how they put it together too. So yeah, it's lots of the nice things about what an article should be. Instead of getting into all the nitty gritty and saying, instead of saying like, oh, the algebra is going to be this, then with this trick, we flip we take the reciprocal and then we flip it one more time. It's like, oh my gosh, okay, crazy. This was very nice. It didn't treat me like I was stupid. It just told me what was going on, right? So I liked it. I liked it. The article doesn't hold my hand with the math, and the math is relatively simple to follow anyway. I wonder what the improvement for pins over normal data-driven learning is. It seems like you wouldn't use this if you have plenty of data to work with. You would use this if you don't have plenty of data, but you do have a physical model. Especially if you know like the physics solution to it. But you're trying to create like a farce, like a fake analytical solution to this. You know, with the losses and stuff like that, but you would do this for things that you don't have exact solutions for. But maybe you have a PDE that is fairly complicated, and you iterate with that math as well, and then make it work with it. And then you follow it and see if the trends are basically the same or not. And that's pretty good. The few magnitudes of loss, that's not bad at all. So maybe like if you have a network trained specifically on some sets of data, tons of sets of data, this is not going to be the bad thing. This one is pretty nice. Doesn't hold my hand with the math, and the math is relatively simple to follow. Anyway. At first I thought this would be an intimidating article about neural networks, but since this was physics based, like the article mentions, we learn how this works as well as what falls short. This is a valuable introducing pins to people that are interested in solutions to problems without needing to know a ton of mathematics. Yeah, basically I really like this because it didn't have to break down all of the math. It just said, this is what this does, this is what our margins are, this is how things work, right? And then even the examples. So interested in solutions to problems without needing to know a ton of mathematics or physics to understand it. The sources / links provided are handy when we want to learn more about an aspect of this article / model. I think, yeah, this is, and then giving the description, the disclaimer saying this is just a tool, not a replacement. I can also appreciate that this model, this pin model, is still only a tool next to lots of other neural networks and other methods. You think that's cool? Watch this. I'm gonna make you guys explode. Ha! I got Stooky. Alright. I can appreciate the model. still a tool next to tons of neural networks and other numerical methods, and should be taught its perks and shortcomings. I found the article interesting. And gives plenty of additional sources to follow up on your own research. Yeah, it was very chill. So I'd say that's very good for an article to not make me feel stupid. Right? Implementing pins in MATLAB. Steve Brunton's YouTube playlist, a broader review. The original paper. Amazing. So yeah, this is like the funny bunny of this is the funny bunny of articles. I don't know, Sticky, have you given any articles maybe like a 9? Because I can't think of anything that this would do that doesn't help me like understand it. This was like relatively simple, but in like a nice different way. I wonder. I found it interesting, plenty of reasons to follow it. And that's the point of some articles. Yeah, because it's supposed to be just like one nice little collection of understanding. I learned something. Okay. I will vote that. Vote that in. I got a 9 on that. Okay. I want to switch this up. I feel like the next one we can do a video. Okay? So let's go back to vote. And now, if I go to non-video, it's going to give me the same one. If we go to video now, then we're going to watch this. Why is root 7 missing? Took 2,000 years to find the real solution. Why? So I'm going to have to pull up my... I believe I have sound on this.
Go for obvious.
Oh, I can hear myself twice.
Reasons. Like, come on, look at this thing.
Okay. So now we get to watch a video, and I get to relax and probably eat my bagels now. Okay? If you guys want to take a quick break, you can do that right now. If you're with me still, then thank you very much. We will be watching a YouTube video. Oh, Rudolph is live. Oh, cool. Let's see. Yeah, I will. Actually, if there was, I wish there was a stretch command, but I'm gonna do that right now. So I'm gonna press play and then be quiet for a minute, and then go with that. All right. So let's watch this together. I'll lower the background music too. Thank you. Alright, go.
This picture went viral a few years ago for obvious reasons. Like, come on, look at this thing. It's a very simple double cube.
The biggest rage bait in math, I swear.
6 lines. They magically happen to create this nice sequence of roots, from 1 to 6. Root 1 is just an edge of a cube. Root 2 is the diagonal of a face. Root 3 is the diagonal of the whole cube, and so on. It's great and all, but mathematicians tend to be greedy. Maybe we could extend this sequence and do better than that? Let's
I tried. You can't do that.
Okay, we have square root of 9, 10, 11, but it leaves a gap, and the gaps are not good. We are still missing 7 and 8.
Oh.
Well, maybe we could add a cube to its bottom? Okay, that's progress. We've got square root of 8. But where is square root of 7? Sure, we could keep piling on those cubes and it would keep producing new lengths, but no matter how many we add, square root of 7 is never going to show up. And the general reason for square root of 7 and for a whole lot of other numbers too isn't some quick observation. It's one of those long-running puzzles in mathematics. This exact question, how many numbers can be found in such cubic solids, kept mathematicians awake at night for over 2,000 years. And it gave rise to the field now known as
mathematicians couldn't sleep.
number theory. So let's jump into this rabbit hole and find out what math is hiding behind this double cube. Take another look at the viral double cube. Let's start by proving that square root of 7 really can't be the length of a segment sitting inside this or any other solid built out of unit cubes.
I think the trick to this, I'm spoiling it a little bit. Basically, you can create every single side length, and if you can make a side length, you can extend it to like the next one. So you see, like right here, this is root 2, and if you extend it to the other side, then you have 2 sets of root 2, right? 2 times 2 root 2. Well, 2 root 2, you can plug that into the root, and you have 2 squared, right? Or root 2 squared or something like that. So then you can plug that in. That's why we have root 8. And then over here, you're just combining different Pythagorean things. And then everything else from there, like if you don't go beyond the 2 or the 3, that's why it's called additive. I think that's why it's going to be the additive number theory stuff. So I'm on board with this so far. This seems pretty nice. So, cool.
But what does that even mean? Which segments are we even talking about here? Look at those 6 lines. Each one starts and ends at a vertex of one of the cubes, and that's exactly the property we want. This segment here doesn't count because it lands on an edge instead of a vertex. A much better way to look at this is to drop the double cube into a 3D coordinate system. The key observation is that the vertices of the unit cubes are exactly the points with integer coordinates. It allows us to drop the cubes entirely and restate the problem. Can you find 2 points in 3D space with integer coordinates whose distance is exactly square root of 7? So take 2 such points, lattice points as they are called, with general integer coordinates k and m and a, b, c. The distance between them comes from this formula, related to Pythagorean theorem. If that were to be equal to square root of 7, the expression under the square root would have to be equal to 7 itself. And since all of those differences are integers, we can rename them and simply write 7 is equal to x squared plus y squared plus z squared. So even though this problem is geometric by nature, the solution is going to come from algebra. To rule out square root of 7 as a distance between 2 lattice points, all we need is to prove that 7 cannot be written as a sum of 3 integer squares. And that part turns out to be surprisingly easy.
There you go.
The fastest route is to look at which squares are even available to us. The first 3 are 0, 1 and 4. All are fine. But now take a look at 3 squared. That's 9, already bigger than 7, so it's useless to us. And every square after that is bigger, so the only squares we can use are 0, 1 and 4. Now we want to pick 3 of those numbers, with possible repeats, that add up to 7. Can we? First of all, we have to use at least one 4, because zeros and ones alone give us the maximum of 3. But we can't use 2 of them either, because 2 4s already give us 8, which overshoots. So it must be exactly 1 4. And then the best we can do is 4 plus 1 plus 1, which is 6. Not enough. Therefore 7 cannot be written as a sum of 3 perfect squares.
Oh man. It's almost like this is like a
So just to recap,
theorem of some kind.
We proved that square root of 7 cannot be found in such cubic-like shape, which means that we cannot do better than that. Now we could call it a day, but as a fellow mathematician, I want more. 7 is not a sum of 3 squares, but numbers 1 through 6 are. So a natural question occurs: which numbers can be split into 3 squares and which ones can't? What do those numbers look like? Is there a pattern, or is it messy like with primes? In fact, this question has a neat short answer, and it is so hard to prove that it absorbed the minds of the greatest mathematicians, Euler, Gauss, Legendre, or Diophantus. To fully understand...
I like how you used the picture, the Legendre? Is that right? The picture of the caricature. If you saw that. Come on, go back. I think there's a few more frames. Yep, I skipped some stuff. I think but I think the answer to this is that there are, you can write literally every other number except just root 7. Root 7 is the only one I think you cannot write. I think that's right. Put the cubes in complex Hilbert space. Well, we'll see if we do. Also, hello, Fook Life. Hello. Hello. And have a good stream. Thank you, Kami. Have a good one, okay? Anyway. Polygons.
The Pythagoreans placed great importance on number theory, in particular on parts related to geometry. This led to their interest in triangular, square, and more generally polygonal numbers which come from geometric constructions. For example, we can build a triangle with side 2 out of just 3 dots. Side 3 takes 6 dots, since we add a new row of 3 to the previous triangle. And so on. That's why the second triangular number is 3, the third is 6, and the fourth is 10. We also define the first one to be 1 and the 0th one to be 0.
I love triangle numbers.
This lines up with our intuition. Side 1 means a single dot. Yep, this single dot is a triangle, and you won't convince me otherwise. And, well, triangle with side 0 is simply no dots, because there's no triangle. In similar fashion you can define square numbers, pentagonal numbers, and so on. Oh, and the square case is genuinely interesting, because those are exactly the perfect squares. 1, 4, 9, 16, and so on.
No way.
The Pythagoreans really were onto something here. They, and many other mathematicians over the years, discovered, or maybe invented, a lot of identities tying polygonal numbers together. For example, that the sum of two consecutive triangular numbers is a square number. Or that 8 times any triangular number plus 1 is a square number as well. Then, much later, in the 17th century to be precise, 𝖘𝖔𝖈𝖎𝖆𝖕𝖎𝖙𝖘, who was also into the topic, took a different approach to those numbers and proposed what we now call Bache's conjecture. It says that every natural number can be written as a sum of at most 4 squares. And that's the turning point of our story. Let's focus on the number 4 here. Is it optimal? Maybe 3 squares are enough. Well, we've seen already that some numbers can't be represented as a sum of 3 squares, the 7 for instance. But are there more? In fact, 𝖘𝖆𝖆𝖆𝖍 proved that there are infinitely many of those, and he did it without even trying to.
You wanna hang a small cube off my
In his magnus opum, Arithmetica, 𝖘𝖆𝖆𝖆𝖍 solved a whole bunch of self-posed problems, but I want to focus on this particular one, problem 11 from book 5. In this problem we want to split the number 1 into 3 parts, such that each of them, after adding a given number a, becomes a rational square. Add those 3 squares together and you get an equivalent formulation of this problem. We want 3 rational squares, each greater than a, adding up to 3a plus 1. Nice, that kinda looks like our problem. And 𝖘𝖆𝖆𝖆𝖆𝖆, while solving his, solved a part of ours too. You see, he stated that the number a here cannot be of the form a to b plus 2. Since integer squares sit under the umbrella of rational squares, his result also tells us something about which numbers can't be written as a sum of 3 perfect squares. Plugging this a to b plus 2 into 3a plus 1, we get that numbers of the form 24b plus 7 are not representable as 3 squares. And that really is true, which we are going to prove right now.
What?
To do that, we need one simple tool, modular arithmetic. It might sound fancy, but it's really just another way of writing division with remainder, where you only care about the remainder itself. Imagine dividing a number n by 8. You write that n is equal to 8b plus remainder r. In modular arithmetic, we would say that n is congruent to r modulo 8. As simple as that. Now, our numbers 24b plus 7 are of the form 8 times 3b plus 7, so all of them leave a remainder of 7 when divided by 8. In other words, 24b plus 7 is congruent to 7 modulo 8. For us, this means that if such a number were a sum of 3 squares, that sum would also have to be congruent to 7 modulo 8.
Makes sense to me.
And here's the fun part. Remember our proof that 7 cannot be written as a sum of 3 squares? Almost the same line of reasoning does the job here as well.
What?
The key is to notice that a perfect square can be congruent to only 0, 1 or 4 modulo 8. Take any square, call it x squared. Divide x by 8 with remainder, so that x squared becomes 8y plus r squared. Expand it and group everything that's divisible by 8. Those grouped terms vanish under modulo 8, which leaves x squared congruent to just r squared. Nice. Now we only have to check the different reminders x can leave when divided by 8, and there are only 8 of them, the integers from 0 to 7. Running through all of them, modulo 8 gives exactly what I promise. 3 options and that's it. Every perfect square, no matter how big, leaves a remainder of 0, 1 or 4 when divided by 8.
That's
now
a bummer.
Take any 3 squares and add them up. The remainder of the sum depends only on the reminders of the parts, and each of those is 0, 1 or 4. So all we have to check is whether you can build a 7 modulo 8 out of them. The biggest sum possible here is 4 plus 4 plus 4, which is 12. While the next number leaving a remainder of 7 is 15, way out of reach. So the only way to get a remainder of 7 is to hit the number 7 exactly. But that's precisely what we ruled out
Yeah, that's impossible.
earlier.
That's literally
Which means
impossible.
A sum of 3 squares simply cannot leave a remainder of 7 when divided by 8, while every number of the form 24b plus 7 does. Therefore we arrive at a contradiction. 𝖈𝖊𝖍𝖈 was indeed right.
Well, there goes my hypothesis. I was wrong.
Something more. Notice that we never used the 3 hiding inside that 24. So the number 24 in 𝖈𝖊𝖍𝖈's result can be replaced by 8, and everything still works.
Oh,
Therefore, no number of the form 8b plus 7 is a sum of 3 squares. This is something that Descartes noticed many years after 𝖈𝖊𝖍𝖈's results were published. And Bachelet, yes, the same one as in Bachet's conjecture, spotted that even the Descartes condition wasn't enough, since numbers of the form 32b plus 28 also can't be represented as 3 squares. But even both families don't give us the whole picture here. There are far more natural numbers that can't be represented as a sum of 3 squares. And the first person to notice this was Fermat.
Uh-oh.
Pierre de Fermat was one of those mathematicians that touched a lot of subjects and stated a lot of conjectures, some of which you may know very well, like Fermat's last theorem.
Which, by the way, that $1,000, that's $1,000, the $1 million prize for Fermat's last theorem didn't get claimed because the guy that's proved it was like, I barely even found something, and it proved it, but it wasn't satisfying enough. So technically, that $1 million prize is technically still available. Well, I mean, no, it's claimed, but they're rescinded, so it's basically gone now. So the other $1 million problems are still out there. But that one kind of got, I'm not sure if they liquidated that one or what the case is, but it's kind of funny how the proof which just kind of fell out of some other math the guy was doing, which was really funny. Pretty cool, and a completely different approach, and it came out almost immediately. I forgot the guy's name, but that's what I've heard. It was it came out really, really easily from the math he was working with that nobody was looking at. And yeah, it's a very unsatisfying proof for Fermat's last theorem. So hopefully he's probably going to cover that right now. I'm also going to make it a little faster so we can actually get to some of this other stuff.
Quite massively. Fermat noticed something brilliant. The two families we just met, Descartes' 8b plus 7 and Bachet's 32b plus 28, are secretly interconnected. The second one is just the first one multiplied by 4. And Fermat claimed we can multiply not only by 4, but by any power of 4, and the property still holds. This
Oh.
essentially follows from this one very simple statement. If 4n splits into 3 squares, then so does n. To prove it, we will use the same modular arithmetic tricks as before, only with 4 instead of 8. An even number squared is 4r squared, so it leaves a remainder of 0 when dividing by 4. An odd number squared is 4 times r squared plus r plus 1, so it leaves a remainder of
My prize
1.
money is not up to
And
today's
these are
inflation.
the only options,
I
which
think
means that
it's
this time the
$1
remainder
million
depends only on the
flat,
parity
right?
of squared number. So
I think it was
4n
Andrew
can
Miles
be split into
approved
3
for
squares,
Miles.
x squared plus y squared plus z squared. The left side is divisible by 4, so the 3 reminders on the right have to add up to something divisible by 4. And out of zeros and ones, the only way to do so is by choosing 3 zeros, which means that all 3 squares are even, and we can write them as 2a squared plus 2b squared plus 2c squared. Then divide everything by 4, and that's it. Here's the representation for n.
Ooh, okay.
Implication works in the way that we can just read it backwards, but we need to negate everything. So if n can't be written as a sum of 3 squares, then 4n can't either. And it means that neither can 16n or 64n all the way up. And since numbers 8b plus 7 can't be represented as a sum of 3 squares, neither can numbers of the form 4 to the power of 8
I think it was Wiles.
times
I think
8b
you're
plus
right.
7.
I think it was Wiles.
Fermat, with this simple observation, generalized those two results into a whole family of numbers that cannot be written as a sum of 3 squares.
Fermat's
And he
theorem,
claimed
TM.
that these are the only ones.
Fermat's
The problem
conjecture,
is,
TM.
Fermat is Fermat. He liked to make empty promises.
It was Wiles,
And
right?
yes, you've guessed it, he didn't prove it entirely, only the part we already covered, which is that those numbers can't be represented as a sum of 3 squares. Fermat never found out why every other number, not of this form, is representable as a sum of 3 squares. And honestly, this doesn't surprise me at all. Not because Fermat liked to complain about margins being too small, but because even the hardest proof of this theorem is still brutally hard to comprehend. And the original one, from the 18th century, absorbed the mind of about every great mathematician of the era.
The
This
goat
conjecture,
meetups.
stated by Fermat in 1636, gathered the finest
I like this
mathematicians
timeline
of the
thing. This
17th
timeline
and
thing makes a lot of
18th
sense.
centuries. Descartes and Lagrange worked on it, taking off smaller cases. And so did Euler, who honestly did a ton of work on this topic. For instance, he found a connection between the 8m plus 3 case and triangular numbers, which he couldn't quite use. In fact, Gauss picked it up 66 years later in a theorem now called Eureka theorem.
Eureka.
Euler also corresponded with Lagrange and Goldbach, and together they got really close to the final proof. But the one who crossed the line was Legendre, who with some ridiculous brute force method finally proved the whole thing in 1798. That's why we now call it Legendre's three-square theorem.
By the way, again, that image right there is a caricature from, I believe, one of his other students. I forgot. Let me look that up real quick because I think it's really funny. Legendre caricature. It was from one of his students. I forgot what or why. It was. I think it was. What's his name right here? I just saw it. This little dork. Yeah, with this dude. That's not Gauss. I don't think it's that Gauss. I just really like this picture. Is that the best picture of Legendre? This is by Fourier. That's right. So it was what Fourier had a caricature done by someone, French artist, and then this is the image of. This is Fourier, and then this one is Legendre. I like that. Pretty funny. I remember doing that during my Wikipedia web exploring.
This result is a culmination of over 2,000 years of hard work done by hundreds, if not thousands, of great mathematicians. It's a beautiful story.
He did it on
a
purpose.
bittersweet one. Bitter
Oh, yeah.
because modular arithmetic is nowhere near enough to finish the job. Everything we've done so far can only ever rule numbers out, not create a representation.
Forgot about math is
Sweet,
used.
because the refined proof, the one that mathematicians reach for today, published by Dirichlet in 1850, pulls out some absolutely exquisite machinery. The first
Dirichlet.
ingredient is the theorem that has famously been proved in over 240 different ways, the law of quadratic reciprocity. The second thing Dirichlet needed was his own theorem on arithmetic progressions, which says that if a and b share no common factor, then the sequence an plus b contains infinitely many primes. And the third and last ingredient were ternary quadratic forms, plus the entire theory built around them. Every single one of those is hard to prove on its own. This is the cost of proving Legendre's free-square theorem. So no, sadly I cannot show you the whole proof today, because that would make this video like 3 hours long. But that doesn't mean it's over.
I mean, that's cool. I really like this presentation, by the way. This, like, I know I keep pausing it, but, like, I really appreciate how this is a nice frame. Really mellow kind of math. Like, this is, like, low maintenance on my end, and I don't feel like I'm learning something absolutely insane. Number theory is relatively simple to keep up with. Except for, like, the proofs, like, the ones we just covered, like, right there. But, I mean, I'm, like, vibing. This is nice. This is a really nice video. Like, I would watch this, turn my brain off, and then, like, learn something as I go, kind of. I appreciate this. And then, like, the presentation with, like, the historical context, that's exactly what I want for, like, a math video. Because, I mean, yes, we can always cover, like, these math topics, but I enjoy a lot learning about why anything happened. What happened in history? What's the deal here? Did they think it was cool? Did they think this sucked? Did they have any prejudices against this? Like, I kind of like learning about that stuff because, I mean, math history is something that never gets glossed at all. So as video formats, I really appreciate this. So I'm giving this one kind of high perks right now. I'm really enjoying this a lot.
It's not the last chapter of this story. Fermat polygonal number theorem is. For context, we'll need to go back to 𝖈𝖃, who, as I've said earlier, conjectured that every number can be written as a sum of at most 4 squares. But there was one detail I deliberately left out. Fermat jumped on this result and stated a much more general conjecture. And I quote, "I was the first to discover the very beautiful and entirely general theorem that every number is a sum of at most 3 triangular numbers, every number is a sum of at most 4 squares, every number is a sum of at most 5 pentagonal numbers, and so on ad infinitum, whether it is a question of hexagonal, heptagonal, or any polygonal numbers." Oh, and here's the fun part. I cannot give you the proof here, which depends upon numerous and abstruse mysteries of numbers. For I intend to devote an entire book to this subject. Spoiler, he never did, and other mathematicians had to finish job for him. We'll start from the end. The pentagonal and higher cases were handled by our Lord and Savior Cauchy in 1813.
Cauchy.
The 4 squares case was done by Lagrange in 1770. But the 3 triangular numbers case is something I want us to prove. We are in for a treat. Just to make sure we're on the same page.
This is gonna be wild, right?
To prove that every natural number can be written as a sum of 3 triangular numbers. We defined those back at the start of this video,
or maybe not.
But I never gave you the algebraic definition. The nth triangular number is the number of dots in a triangle with side n, which is just 1, plus 2, plus 3, and so on, up to that final row of n dots. As per anecdote from Gauss's childhood, to find an explicit formula for this sum, one just needs to double it and sum it in reverse order. Now we can see that each column here sums up to n plus 1,
n minus 1 over 2,
exactly
right?
n columns like that, so the whole thing adds up to n times n plus 1. And since we calculated 2 such sums, we just need to divide it by 2, and here we go. The algebraic definition of the nth triangular number is n times n plus 1 divided by 2.
Yeah, they clearly didn't own a PlayStation.
That every number can be written as a sum of 3 triangular numbers was actually Gauss himself, because who else? And we are going to follow his line of reasoning. It comes down to showing that representing a number with 3 triangular numbers is equivalent
they clearly
to
didn't own an air fryer
we already
either.
know. Let's write n as a sum of 3 triangular numbers, using our fresh algebraic definition. Now we do something rather unintuitive, so you gotta trust me. We multiply both sides by 8, and then add 3 to both sides. On the left as a plain 3, but on the right we split that 3 into ones and hand 1 to each of those parts.
Oh boy.
And here comes the eureka moment Gauss had while writing this
proof.
Eureka. Those 3 expressions are perfect squares, so it connects to Legendre's free-square theorem. And the best part is, this works in reverse too. Do you remember that a square can only leave a remainder of 0 or 1 modulo 4? Well, 8n plus 3 leaves a remainder of 3, and the only way to build a 3 out of zeros and 1s is by getting 1 plus 1 plus 1. So in every single representation of 8n plus 3 as a sum of 3 squares, all 3 squares are odd, which means that we can always write them as 2x plus 1 squared, 2y plus 1 squared, and 2z plus 1 squared.
Then you distribute that, and that's the 4x, yeah, okay.
Therefore,
that's
a natural
cool.
number n is a sum of 3 triangular numbers if and only if the number 8n plus 3 can be written as a sum of 3 perfect squares. And that means
Wow.
we are actually done. Legendre's free-square theorem tells us that the only numbers missing such a representation are those of the form 4 to the power of a times 8b plus 7.
That
And
sucks.
8n plus 3 is never one of them. So 8n plus 3 always splits into 3 squares. And n always splits into 3 triangular numbers. That's the Eureka theorem done.
That's
And
cool.
with it, the theorem this whole story was building to, the Fermat polygonal number theorem, is finally complete.
Wow.
And that's where our journey really ends. Or does it?
Oh, well, we
We've
got the other
mainly
one.
talked about 3 squares case, but what about 2 squares or 4 squares? How do you tackle those? Also, representing integers as sums of polygonal numbers is a classic problem of additive number theory, a standalone field of mathematics full of magnificent results. Even my own future is tangled up in it, because in October I'm starting a PhD on topic that has me using Legendre's free-square
Aw,
theorem all the time.
Congratulations.
Case
I
in
don't much
point
care
that
for number
this
theory,
subject
personally.
And this journey is far, far from over. Who would have thought that this silly picture hides so much mathematics?
I think that picture is just a rage bait picture, I'm not gonna lie. All the time I see it, I get so mad, because it's way too much to cover. Pretty cool. I dig this. This was a very chill video. I liked it. I wouldn't say this is, like, absolutely outstanding. Well, I would say this is pretty good. I would give this, like, a comfortable... What would I have flaws with on this video? It was good. Hi, Tyler. Go enjoy your lurk. I would say, like... I mean, yeah, we didn't have to... We hand-waved a lot of the mathematics. We didn't have to, like, understand, like, every single proof. Especially, like, the crazy ones that were proving all the cool stuff in the later end. Like, Legendre, what he did. But I appreciated how we did the basic stuff, and then we contextualized a lot of it, and then we had a lot of historical context, and then we covered, like, well, why does this work? Why does that work? This person was trying to solve this, and then that was left open, and then this other person solved this. It ties in the web of mathematics as, like, something that is actually kind of tangible. So I appreciated that. Actually, I'm gonna give this an outstanding. I thought this was very good. I thought that this was very, very nice, and it was very mellow, all things considered, right? I feel like I got to watch something without needing to stress too much about it, so that was cool. So let me think of what to say with this, and let me get the music back up. Let me say this. This was an excellent video, not only introducing a topic that seems relatively simple, but also introduces math history in a digestible and interesting way. Right? So we got another ad in 3 minutes, although I can do this like review real quick, and then we can move over to another non-video submission. But yeah, while you guys look at the caricature of Legendre over here. This is the Fourier. Maybe if I open it to the side. So dumb. Legendre. I should make these emotes. I should really make these emotes for the chat. That'd be really funny. Not Gauss. This is not Gauss. This is Fourier. Fourier, and then this is Legendre. Pretty hilarious. I liked it. I liked this video. This was like, and then I will subscribe. That was pretty good. Yeah, see, look, very pleasant. 220 something views. As to why should I care about this math, I don't care. But I think it's cool, and someone needs to learn about this stuff. So I liked it. It's like high fashion. Maybe during after stream, well, when everyone moves over to the next one, I'm gonna take this little crop, and then I'm gonna make that an emote. That's what I'm gonna do. Okay. Excellent video, not only introducing the topic, but it seems relatively simple, but also introduces math history in a digestible, interesting way. There's clearly a progression about this history that was intro that doesn't get covered in a meaningful, it doesn't get covered often. I felt this was a very relaxing video that didn't demand too much from the reader, from the watcher, while also enjoying a informative video with, how would you phrase the stakes of the thing? Caricature videos? Like drawing the caricature, or like yeah, like the art of this guy. I'm gonna get this later, don't worry. But this is a really relaxing video. Didn't demand too much of the reader, while also enjoying the information. I felt the math was easily digestible while not being too... My friend is actually a caricature artist. I should invite her one day. I should invite her one day to do, let's say, an art caricature. Let's say a person or something. But she does that. I think she's still where she's at right now. She works at an amusement park as a caricature artist. She's pretty cool. We went to high school together. Make a caricature of Aleph. I could ask her to do that. I could always do that. I could be like, hey, I need, grab her, shake her down. I need an art. I will pay you. And she'll be like, pay me what? I'll be like, money and exposure. I think she still streams. I could always check in, but I'm sure she's doing like her art career right now, trying to figure that out. One art, please. The math felt very easily digestible while not being too, and showed how each step makes sense. I wasn't bogged down too much with the notation. Yeah, because I don't think there's any manum in this video as well, right? Like, there's absolutely no manum, right? Or was it?
3 squares? Almost the same line of reasoning does the job here as well. The key is to notice that a...
No, it looks like it's animated by hand, which is something that I would probably do. That's cool. Wasn't bogged down too much with the notation or examples. The history was the centerpiece. How would you phrase that? Like this is like a plot A and plot B kind of narrative storytelling. So as much as we wanted to get to the solution, I was also curious about the history, right? It was a side plot, yeah. It was a side plot of the video, which made the discussion even more interesting. It took stress away from all the math and wanted to make the characters in history relevant to the story. I can't spell. since these theorems come from them. Hi, famished. Are you potentially famished today, or are you definitely famished today? Also, you have your remote. Don't forget. Exclamation point famished. You have your own command. Don't forget. We're doing our math videos today. Reviewing them. We just finished one about the rage bait video. The square root 7 doesn't fit in this. It's kind of cool. Theorems come from actual names of people. Yeah, I made that a long while ago. Don't forget. Yeah, I figured you would like that. Let's see. The theorems come from theorems. Names come from these mathematicians. It makes sense to cover them in greater detail and show the collaborative effort between them all. Oh, okay. Not feeling like math today, just do some editing. No worries. Really chill day on my end too, because like Stuki finished their end of the reading these videos and ranking them. I was supposed to have a guest today, but he couldn't make it, so I'm just doing my own thing. So in this case, I'm going to be going to a non-video. So I'm going to going through an article and then see how good or bad that ends up becoming. Let's see. I don't think I can really phrase this video as being any better, or like I don't think I can name anything that was that needed more help. Like if anything, like this specific question, I hated this question personally. Like I genuinely hate this this meme because it's such a rage bait kind of thing. Because I've seen, let me show you the art that I've had saved to. Just because of the phrasing, it kind of pissed me off. So it was, here it is. It looks like this. OMG, there's no way to obtain 7. Oh my gosh. Okay. And then you would this would be on like one of those like what do you call it, engagement accounts. So it was just like, OMG, it's impossible to get 7, and then just like exclamation point, and then like blowing head emoji. And I'm just like, yeah, engagement bait. That's all it was. I was just like, I hate this particular question because it's so freaking annoying to see. Like it actually bothers me. The specific meme bothers me. Though at least the art that I'm showing right now. Genuinely, I hate this. But the question itself is okay, and if people treat it as like a humble question, then I'm okay with it. But that's just my gripe, my personal gripe with this question. But yeah. Also sharing a meme to get the gist. Hold on. How do I phrase this? I'm not mad that they used the meme, but I'm mad that this meme was the one that taught me something. Because the original meme that I saw actually pisses me off. Breaking down a popular math meme is always a fun way to gauge a video in the beginning. I do think I hate that meme though. I will give it an 8.9 just because it used that premise. Other than that, I think that's fine. Great animation style, non-manim, and good use of the historical timeline of mathematicians. Yep, I don't think I have anything else to say. I will vote that now. Locked it on your phones. Okay, so we have the choice between two things right now. I'm gonna leave it as a poll real quick. So the question is, what next? Do you want to do an article or do you want to do a video? I'm gonna go get some more coffee. I'll leave this for 2 minutes, and you can vote. Vote on your phones. So if we do another article, let me reload this page. If we do another article, this is the Math is Beautiful with a little pet project with visualizations. This seems kind of cool. Or we're going to cover the Vladimir Arnold's Rainbow as a masterclass in simplification, which covers the topics for literally every single child in the world, except elementary kids, because they're not children. They're not mathematicians yet. I'll be right back. I'm going to get some coffee. Coffee. Vote on your phones. Okay, I'm back. Sorry. What won? What won today? Let's see. Yeah, so what was the result from the poll? I couldn't see it. Oh no. So are we watching an article? Are we reading an article? Or are we watching a video next? Oh, hi, Stuki. It was a tie? Stupid. Okay. How'd you get 100 exactly? I'll vote non-vid. Okay. Then we're gonna do the article then. So, thanks, Stuki, for the tiebreaker. We're gonna do this one then. Also, I got my coffee. I didn't get to add any cream or almond milk. I just got sugar. So we're gonna be going and through this video. This here says spent a lot of your points. Sorry about that. They should be worth 1 point. But you can get more if you're a channel member. Wait a second, Tyler, you're not subscribed. No, you are. Wait, are you? I don't know. Anyways, math is beautiful. It sure is. Sure is. Let's see. There's a little pet project that features visualizations of mathematical concepts as colorful images or animations, generated using short Python scripts. Each of the entries includes a short explanation about the mathematics or physics that motivate it, and a link to a GitHub repository with the scripts that can be used to generate them. The goal for me is to cover... The goal for me is to cover as many different topics as possible, as long as they're visually appealing, and they make the codes as short and self-contained as possible. To this end, most of them are use just NumPy, matplotlib, and the occasional scripts SciPy or PyTorch. I started publishing these visualizations informally on my Instagram channel, but this summer I've decided to compile them in a website format, even though making the actual images has taken me longer than just this summer. Ooh. I think in terms of in terms of content, I'm not sure if you can't use anything from last year, and I'm not sure if you can use things that are longer from like a year ago. But at least it's not like a part 2 kind of video, because one of the videos we covered yesterday had like a part 2, and you can't have a part 2 to like a self-contained video like a submission. You can have some kind of context from like your other videos and say this is the big one, or whatever the case, as long as you are able to cover what the video is. But I'm not gonna scrutinize this to that extent. I think it's pretty chill. So yeah, but some of the videos I noticed that like have like a tie-in. Like yesterday, we had a video that sucked. It has to be made within the submission period, within the 6 months. Yeah, I would believe it. Like I'm not gonna. Python, it's relatively simple, so like if you worked on this for quite a while, this makes sense. I'm okay with that. I'm just pointing out that like we saw a video yesterday that I feel like should have been like disqualified, because it said for explanation of something else, watch this next video, when that you shouldn't be doing that. You need to be like you shouldn't be tying in another video in the video that you covered, in the video format at least. Anyways, there's 65 of them already. I'm not that fast. The webpage is new. I hope this still qualifies for this edition of Summer Math Exposition. No AI. Fantastic. 100% human coded in this case. Even if it does not qualify for the actual competition, I would love some feedback. I will give you your feedback, my friend. So let's go ahead and click it. So it looks like we're going to cover the different kind of visuals. And honestly, as a Vtuber, I kind of want to use some of these visuals, because making math look cool is really hard, right? So yoink. No, but this is fantastic. I might want to reach out and suggest I would like to grab some of these. Okay, gallery of mathematical visualizations. Started this project, blah blah blah. No AI. Use it for my own logical and mathematical training. In the early portion of this collection, I was featured in the post in the Spanish blog 𝖘𝖔𝖈𝖎𝖆𝖕𝖎𝖙𝑘. Let's see what this is about. Las matemáticas son bellas y estas me imágenes los demuestran. I wonder when they did this, though. This is a Barcelona, dude. That was a year ago. Okay. So, I'm only skeptical now. If you have wrinkles, what? I'm only skeptical now because if this was done before the year ago, I'm not sure if this qualifies, which is probably what they're suggesting, but I would give this the benefit of the doubt, but I'm just going to go through these as they look. So the Mandelbrot set. Mandelbrot set is very cool. Everyone knows what the Mandelbrot set is. Z squared plus C for some threshold, and then you can generate it. That's really cool. View the code on GitHub. I want to know how you made this. So you're using NumPy. Okay. Yeah, I don't know why I was thinking that this was like made with Turtle or something. Oh wow, 24 lines, really clean. Cool. The colors are nice. I like it. Everyone knows the Mandelbrot set. The fern. The Barnsley fern. There's a new fractal. The Barnsley fern. It's like, I just know this as a fern. I'm not sure if that's quite right. Resemble the portions of the Aspilium adiantum nigrum, as we call it in the Catalan, l'alfàcia negra. Slight changes in the parameters allow you to mimic all kinds of other ferns. Ferns are fantastic. This structure was published in the 1988 Michael Barnsley book, Fractals Everywhere. I should get that book. That sounds cool. Code looks relatively simple, I hope. This looks cool. Save the figure as a picture. Nice. Total iterations. So you make an array of these. Hold on. What's actually happening? Something, something, thrown something, something. I added a few books recently too. So if you wanted to check them out, I added Gun Germs and Steel. And then I added another one. Forgot what. But it's another one of those like science discussion books. Yeah, okay, this looks nice. It's a fern. Oh, this one's is the attractor stuff, isn't it? Oh, these are so cool. This is so cool. The Lorentz attractor, perhaps the most famous chaotic system of differential equations, the origin of the popular concept of butterfly effect. The metaphor may be inspired by the resemblance of the Lorentz system solutions to a butterfly. Butterfly effect, that a butterfly flapping its wings in Australia can end up causing a tornado in North America. The metaphor to exemplify the chaotic behavior, the atmospheric dynamics, in which small changes in the initial conditions can cause very different outcomes. It's created in this place by Edward Lorentz, Ellen Feder, and Margaret Hamilton as a simplified meteorological model of atmospheric convection. It has a very interesting property that tiny variations in the initial conditions result in completely different solutions as time passes. I wonder how you made this. Because, okay, these are all made without Manum as well, which is something I can appreciate. I don't hate Manum, it's just like everyone uses Manum. Does that make sense? Right? Everyone uses it. So for us to like have things that aren't just Manum is cool. I like that. So matplotlib animation. You can have just animations? I didn't know you could do that in matplotlib. Holy smokes, if that was the case, I could be doing a lot more coding stuff. What am I doing? This is amazing. So you get to show what frames you want. That's cool. You can save it as an MP4. Cool. I like this. I also like the colors. These are really nice. If I could have this like as a literal print, like a 3D print in some way somehow, like the 2 discs and everything, that'd be amazing. I like this. Let's go for some of the cooler ones. So the Noon Fractal, this one is you're trying to find non-intersecting stuff, right? And so to do that, you have all of these repeating, not really touching you kind of things, right? And then it becomes like a fractal, a different kind of fractal. This is like the Julia set, right? Initial guess will determine which zero the method will converge to, if any. This fact becomes particularly interesting when used in its own complex functions. Each of the roots, and by the way, I'm gonna bookmark this because I think this is great. Recommend sequence. Recommends sequence. I don't know what this is. What is this? So you have this little trail back here, and then they all spin, and then it goes back into another trail, and then it goes to the bigger trail, and it goes out here, and then it goes to this bigger trail. I don't know what this is. It's defined in a very simple way, but it has a very strong tendency to produce aesthetically appealing, spelled wrong, appealing results, which it is used. It was first described by the Colombian mathematician Bernardo Recamán Santos. The semicircle representation in the picture is a variant of the one created by Edmund Harris for the excellent YouTube channel Numberphile in the 2018 video, The Slightly Spooky Recamán Sequence. Its definition uses a simple recursion relation. You start with the term a naught equal to 0, you find the nth term, and you try to add n to the previous term. And check for the result. If the resulting number is negative, it is already in the sequence, you subtracted n instead. Or it is already in the sequence, you subtract n. The resulting number is positive if still unused, and you take it in as the next term. This way, the first terms are 1, 0, 1, 3, 6, 2, 7, 13, 20, 12, 21. There exists an open problem based on a sequence. Niels Sloan conjectured that every positive integer is a term in the sequence. It has not been proven, or disproven. Want to give it a try? I like that. Give me some context as to this question. I don't even know how you make this picture though. This is kind of cool. I'm gonna go through a few of these kind of quickly because some of these ones I kind of know, some things I don't. Like the moving sofa problem. Making an animation of this is actually kind of cool. Arises on a very simple question has not been rigorously solved. Find a two-dimensional shape that with the largest area that can slide through an L-shaped corridor. Yeah. Is it in fact going to be this sofa? This first mentioned by Leo Moser in 1966. I like the context. I like all these little contexts, these little blips. Only in 1992, Joseph L. Gerver was able to come up with a better bound, which we believe to be extremely close to the actual sofa constant, 2.21953 something. However, the exact value is still unknown. Woo! Been found this sofa has been found by an artificial neural network. The network is rewarded for increasing the area, while being penalized when the sofa overlaps with the walls. Divide this algorithm on article for recreational mathematics for the Spanish magazine Investigación y Ciencia. Unfortunately, now disappeared. That's a bummer. So you seem like a very competent individual, Don Raymond, or La Raymond, dude. I don't know. They're cool. Trapped Knight is not a map of Treasure Island. Instead, it's actually not even an island. It's a surprising exercise related to the game of chess. What? The Trapped Knight problem. This problem was invented by one of the many mathematical heroes, Niels Sloan. Hey, I've heard you before. Explains it very well in the Numberphile channel. I think you're a fan. Gives rise to the entry A316667 on his online encyclopedia of integer sequences. So this seems to be like some sort of sequence, and we have to approach it in the middle. We start with the center square. I also like that there's some errors in spelling. It's fine. Oh, pardon me. Oh my gosh. I need a drink. I need some coffee. The idea is to label the squares with a very large chessboard with the natural numbers following the spiral. We start with the center square with the number 1 and then place the number 2 to its right and continue turning clockwise in the outward spiral. Dying's bad for my... I know. Then we place the chess knight in the center, which can jump in the usual way, 1 square in one direction and 2 in the other. The knight just keeps jumping, always in the lowest number available. Without repeating at any square, the figure shows the path of the knight, which follows this sequence. There's an X over here. However, the knight gets trapped after 2015 jumps at a square number 2084. There are no available squares for the knight to go to, and the sequence ends. In the picture, you can see that it's a square marked in a red cross. Oh. See, that's kind of neat. I like these kinds of questions. They're kind of weird. They're just cool. They're just kind of neat. So I imagine you run a simulation on this and then find out. You can probably find like generic terms. If your knight moved differently, would it be able to do? Would it be able to solve the spiral or this? These are the knight jumps. Okay, yeah. I and J side. I forgot double divide. I forgot if there's like mod 2 or something like that. What does double divide mean? Is it like a... I forgot my Python. Oh my gosh. Because the show I don't do it often at all. Isn't it like the floor or truncates it or something like that? Integer divide. Pretty cool. This looks cool. Turing patterns. This looks like some sort of like cellular growth or something. Or path making. Alan Turing published his famous paper, The Chemical Basis of Morphogenesis. Oh, that's the one where he talks about like cellular automata, right? And reconstructing animals and people, or like evolution as like a program, right? We tried to reproduce the formation of visual patterns in nature, such as the skin on many animals, purely mathematical way using equations for chemistry. These partial differential equations are generally known as reaction-diffusion equations as the model, the diffusion for several chemicals, as well as the reactions between them. Surprisingly enough, the reaction-diffusion equations can be found to reproduce a large amount of animal skin patterns, such as zebras, leopards, giraffes, corals, and fish, just to name a few. Such patterns are now called Turing patterns. That's cool. Simulation is particularly interesting as it ran a couple minutes on a GPU, unlike the standard CPU, or CPUs have parallel computing. Yeah, okay, I know what that means. Blah blah blah. That's cool. Some of these are. I'm still only touching a few of these. There's a lot of context to these questions. I actually really like these. What's this one? Hyperbolic stuff, right? It's a very particular geometric. Hyperbolic space is a very particular geometry that has constant negative curvature everywhere. So as we approach the ends, that's approaching infinity. The picture shows uniform tiling on a Poincare disk, which results in a conformal compactification of two-dimensional hyperbolic space. That's cool. Basically, I'm gonna cover lots of these just based on how cool they look. But there's a lot of really cool questions here. Oh, this is a cardioid. I think you make them as far apart as possible, so that to that is the same distance to each other. And then you rotate this across, okay. In the case with light rays, envelopes, known as caustics. Oh, they're caustics? Is a heart. This is kind of cool. I really like the animation for this. Really convenient. The ambidextrous sofa. So instead of going around one corner, you're going two corners now. That's cool. Oh, the Romanesco. The broccoli. This is the broccoli. This is the broccoli. If you don't know the Romanesco. Broccoli. Cauliflower. There's a cauliflower version. It's the thing. It's the thing. It's the fractal broccoli. And what's weird is that's real. Yeah. Look at that. Look at that. Nep. 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 Yummers. So they made this, like any cauliflower, it has an inflorescence, which means that the meristems are neatly arranged in logarithmic spirals around its axis. Similar way as some flowers, the number of such spirals is usually the Fibonacci number. In other words, the something phyllotaxis, something plant stuff. Pretty cool. This looks like some sort of lift and drag thing. Very cool. Let's go back up in like order. This is the, if I remember, this is that one about predator-prey models, and then for some reason it blows up. Yeah, growth rate of R. As generations pass, the value X can fall into 0. Species extinction, stabilize at a constant population, oscillate between several population values, or even exhibit chaotic behavior. For R above 3, the system starts oscillating between 2 values, then 4, 8, 16, 32, and then reach the value of about 3.56995, and the population becomes chaotic. It remains like this except for some islands of stability. That's weird. That's some weird stuff. This is weird. What is this? Factorization diagrams. According to the fundamental theorem of the arithmetic, every integer greater than 1 can be uniquely decomposed as a product of primes. This theorem is already indirectly stated in Euclid's Elements. The picture shows an intuitive view of the prime factorization of the first 49 integers. As far as I know, this type of visualizations were first created by Brent Yorgi. I like these diagrams as they seem to support the vision of Daniel Tammet, who described prime numbers as smooth and round shapes similar to pebbles on a beach, in his book Born on a Blue Day. Okay. In the case of our picture, prime numbers do appear as simple chaotic dots, simple circles of dots, without any inner complicated structure. As I like the mountains better than the beach, I didn't choose pebbles, but I made them look more like blueberries instead. Okay. That's fine. So 1's prime, 2 prime, 3 prime. 4 is not prime. Right? So 5, 6 is 2 and 3. 7's prime. Wonder why 4 looks like that then. 6. These are very weird shapes. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 times 3. 8 is 2 sets of 2 by 2. 2 by 4. Oh, whatever. This is an interesting way to draw it. I kind of like it. Okay. The Collatz conjecture. I'm not going to cover this one, but this is cool. These pictures are just nice. There's a lot of context to these questions. Brownian trees. Yeah, this is like every kind of like major math visualization model that you can show and think of. And I appreciate that there's codes that go to all these things. That's actually really fantastic. So if anyone has any questions about these particular shapes or models, you could just get into that. The Goldbach's conjecture states that every even positive integer except 2 can be written as a sum of 2 primes. Remains unproven to this day. So these are the numbers. I think these are the numbers that they use. It's called the Goldbach comet. It shows the number of ways of decomposing each of the first 50,000 even integers into primes. That's cool. This is the dragon curve. That's the burning ship. Rock, paper, scissors. I don't even know. I'm guessing it's the color. A cellular automata. Okay. So one of these colors beats the other, and the other one beats the other, and the other one beats the other. That's cool. It resembles a chemical reaction, the Belousov-Zapotsky something equation. Voronoi diagrams. This is definitely a weird way to look at Voronoi. Yeah, this is actually, hold on, this is cool. When you have a set of points in space, each point has a region in which it's closest. Drawing the boundaries between such regions gets you the Voronoi diagram of the set. The most famous are the ones in 2 dimensions, such as the one in the picture. Blah, 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 blah. To make it more interesting, in this case, I use a color map to plot the difference in distance between the 2 nearest points, normalized by the largest distance. This provides a continuous variation of values from 0 to 0 at the Voronoi boundaries and 1 at the reference points. The color map should remind you of the Pride Homunculus from Fullmetal Alchemist. Look out for him lurking in the shadows. Cheeky smiley face. This is a weeb. You weeb. I like it. If you guys don't know Pride Full Metal Alchemist. That's really cool. I really like that. I like how shamelessly he is about it. He got like this cool, like, shadowy mouth, and is a kid too. Spoilers for the show, I guess. I like that. That's cool. That's really cool. I hate that kid. Nice. See? Bunch of nerds. The 𝖈𝖗𝖊𝖉𝖎𝖙𝖘. Like the 7 chakras or something? That's cool. Burning ship. The anti-𝖈𝖗𝖊𝖉𝖎𝖙. Nice. Game of life. Conway. Yeah, I think this is cool. I'm not sure of how this stands up as a Tower of Hanoi. I'm not sure how this stands up as a mathematical submission, because some of these ones they must have been using these for quite a while. So this seems like more like a gallery or museum. So I'm not sure how much of this is original material as opposed to stuff that they made specifically for this competition, because it seems like they're throwing this stuff in as something that they have been working on, and then they just happen to be putting it together. I'm not sure where that lies in the rule book or the rules. But I think this is cool. So 1 entry per creator. Entry should be self-contained, not part of a series, playlist, or larger project. Something that can dive into without needing extra context. That's fine. Can I use an old entry? Not the old entry. Let me see. It says here, it has to be something new you make this summer. The spirit of this is to encourage people who have never put stuff online before. If you want to work on something you've sort of started once before, that's probably fine, but it can't be something you've already published before this contest. Optimally, you'd use this as a chance to try something new you otherwise might not have. So, on that ground, I won't think I can rank this very high. I'm gonna rank this as like I would say a 6.75. I think this is like a fantastic gallery, and it gives a lot of actual insight. Oh my gosh, these are so cool. I am gonna save this. So I will say constructive feedback and say this is a very fascinating and amazing visual gallery. I can appreciate how these visuals are made and how you've put a lot of effort into most of all these submissions or these visuals. Providing code is your way of showing proof of work and letting people learn about what each of these visuals come from. I feel this is a incredible resource for people that don't know the beauty of math. Can I put this link in the chat? You want this one? You want this one? Yes, absolutely. So, actually, I'll pin it just for a sec. Pin that. So this one, again, I think this is great. I really, really like it. I just don't think this is exactly what the competition wants, because lots of these are probably things that have already been published before,
in like their other articles and things, and how, you know, the timeline of some of them. I don't think that's appropriate. I think it's really cool as a showcase, as a gallery. So if they want to maintain this as like a website's, like the website's opus, I think that's fine. But in terms of the competition, it's like preparing a lot of stuff. Like, it's like putting your resume and saying that that's what your submission is. It's like, it's not kind of not fair. So I'm gonna say I would have to dock it for that. I think it's really cool. Actually, I'll be a little generous and say 7.05, a little more than 7, because it's better than most. But I can't comfortably say that this is appropriate. So I'll just have to tell them otherwise. Very fascinating. It's an incredible resource for people that don't know beauty of math. In fact, I would like to be sharing this. That's not weird to say, right? I like this. This is fantastic. Except, in fact, I'm gonna use it. I'm gonna yoink it. However, I can't just let this be the competition piece, right? In fact, I would like to be sharing this. I would like to share, excuse me, this with others, since it's an incredible collection. However, I cannot, a new thing. However, in good faith, I cannot give this a higher grade, as most of these submissions come from other existing publications you've done, as well as plenty of codes you've shared before. Clearly, this is valuable. No, how do I say this? Clearly, you have learned a lot from these, and that should be held as very credible and interesting and respectable. However, the scope of this competition is to share projects that are new to this summer and shouldn't share submissions from the past. In that regard. So yeah, I like it. I genuinely do like it. Don't let this discourage you, as I can see there's an immense amount of work you've done to make these visuals, and you cite where they come from and how they are generated. That is much better than simply sharing cool images. I liked the Voronoi Full Metal art. Yeah, because it's basic. It's straight up just Pride. It's Pride from Full Metal. I like it. This is cool. They even say so. That's cool. What a weeb. But yeah, I would say this is good. But yeah. Overall, fantastic. Gallery and collection. However, maybe not the best for a competition like this. I still will share this whenever I can. Heart. Alright, I think that's good. I think I can just say that. That's enough. Citing your sources, the little blurbs are really nice. Yeah, and if you guys want to share this, this is amazing. Very good demos. Yeah, see, like, this is like a 48 thing. That's so cool. Lots of code, lots of projects. We can do some more with this stuff. This is cool. Alright, I will submit that, and that's in the world now. Okay. We have the choice between another video or another article. I kind of want to watch another video. I think I might have seen this one too before. Hold on. No, I don't think I have. What makes a number system? This is for undergraduate and graduate level students. We're talking about quaternions, octonions, normed division algebras. In this article, we look for algebraic systems where multiplication rotates and stretches space. That constraint ends up the more restrictive ones than you might expect. So I'm curious about that. Octonions, quaternions are really nice. But the next one I'm going to want to watch a math video. And that means right now. So Vladimir Arnold's rainbow is a masterclass in simplification. So this is about optics and rainbows. What's prettier, rainbows or math? Good news, you don't have to choose. In this video, following many cues of Vladimir Arnold's book, Mathematical Understanding of Nature, I attempt to explain the rainbow in a self-contained way without assuming any calculus or trigonometry. Arnold's approach is remarkably simple, accessible to anyone, with a bit of patience really, yet it can explain many of the complexities of the rainbow. In this video, we see why the rainbow always appears at the same angle, why that particular angle, and why it seems what appears to be lit from below but dark from above. You persevere. There's also an Easter egg at the end. An Easter egg. Alright. We will watch a video. So let me... Oh my lord, that's a 38-minute video. The roll shake. I don't think it needs to be... I don't think it'd be that long, right? Is there a topic restraint? Not topic restraint. I'm fairly certain it was only like 35 minutes is the longest you can go, right? I don't recall. I honestly remember seeing something like that, but I don't know if there was any. Maybe it was in the Q&As or something. Does it have to be in English? Yes. Do I retain ownerships? Yes. Can I have ads? Yes. There's no length requirement. I would say, unfortunately, except if they stated a cap, and you know, a bunch of folks cluster right at the cap. Okay. I almost remember there being the... I guess it probably was from something else. Oh well, I think that's fine. In that case, I'm gonna have to crank it up because atmospheric science seems really cool, but I think it's... I'm gonna have to crank up the speed to get through this. Let me lower my background music. And then hopefully this whole thing loads up correctly. Forgive me. I'm gonna do 1.5 until they talk too much.
Vladimir Arnold was one of the most prolific mathematicians of the 20th century.
Forgive
After
me.
his passing in 2010, one of the many obituaries penned by his peers hailed him as perhaps the last mathematician who could move freely across almost the whole of mathematics. What fascinates many people, myself included, about Arnold's work is how salient its motivations were. For Arnold, even the most deeply abstract contribution was part of an attempt to understand nature. His work illuminated our understanding of diffusion, fluid dynamics, planetary motion, and much more. Arnold's philosophy was that mathematics should be inspired by nature. He was a known and harsh critic of the Bourbaki school, blaming them for what he described as a catastrophic split between mathematics and physics. Besides his contributions to mathematics, Arnold was also a legendary educator and author who wrote for a wide variety of audiences. But in my opinion, few books capture an affection for simplicity quite like Mathematical Understanding of Nature. A collection of 39 short and sweet essays, some no more than a drawing in a single sentence, that are a masterclass in abstraction, simplification, and approximation. I first read it about a year and a half ago and it immediately became an all-time favorite.
Okay.
I admired Arnold's focus on common sense. His ability to extract only what's relevant to the problem at hand and discard the rest. I honestly love this entire book, but I was particularly moved by chapters 5 through 9, in which Arnold analyzes the phenomenon of the rainbow from first principles. It stood out to me as the only calculation in the book which appeared as a sequence of essays, each of them short and self-contained and simple. But somehow, without me ever hardly noticing, the entire complexity of the rainbow suddenly became obvious. And while I perfectly understood each step in Arnold's computation, it took a few weeks of reflection before I felt that I truly understand and appreciate the way Arnold chose to conduct his computation. These essays were not meant for a general audience. They are dense, sometimes a bit terse even. For mathematicians, trying to get into Arnold's head and filling the gaps ourselves is part of the fun. But I find Arnold's telling of the rainbow much too beautiful to be locked behind technical difficulty. So I decided to make this video, doing my best to take you through Arnold's argument, filling the gaps as clearly and faithfully as I can. Hopefully affording you a remarkable explanation of the rainbow, simple enough to doodle on a coffee shop napkin, but precise enough to explain many of the nuances of the rainbow, and actually, a bit more.
I like that. So this seems to be like an ode to the Vladimir Arnold, which is really cool because I don't know this gentleman. It sounds like he does a lot. He did a lot in like natural science, mathematics and natural science, if you will, and that's cool. I can dig this. I can dig the entire thing. I see the scope of the project. I see what we're learning about. So, beginning impressions so far are pretty high, pretty good. I like this so far.
Our story begins on the beach. You are lying on the sand, enjoying the breeze, when suddenly, someone calls for help.
Help!
You quickly prepare to run straight towards them, but then you realize you swim much slower than you run.
Help!
So what direction should you run? If you go in a straight line, you spend too much time in the water. Taking a huge detour to run most of the way along the sand might slow you down even more. By considering many paths at once, we notice that there is a sweet spot, a particular starting direction that will take us from A to B the fastest. But two things remain unclear. How do we find this optimal direction? And what does any of this have to do with rainbows? The answer is Fermat's principle. Fermat's principle decrees that light
Fermat's at it again.
the fastest path. So solving our beach problem is actually the same as working out how light bends as it hits the surface of water. Now, from a modern perspective, Fermat's principle is not exactly a first principle. It raises an uncomfortable question. How does light know the fastest path in advance? Answering this question forced us to completely reform how we think about how light interacts with matter. But when considering large-scale phenomena such as the rainbow, it is usually perfectly reasonable to take Fermat's principle at face value. So the decision we had to make on the beach is exactly the same as the decision light makes when it bends on the surface of water. Working out the solution will yield a fundamental result of classical optics known as Snell's law, so called after Lord Snellius, who recorded it in the late 1600s. Though since then, historians trace it back to Baghdadi scholars around the turn of the first millennium. Snell's law is the most fundamental fact about how light interacts with water, so it is a natural starting point for our exploration of the rainbow. We will see.
Fun fact about Snell's law, in terms of optics, I think this is the one where you have that, like, if you had like several different mediums, let's say like oil and the water and then all these different like layers of stuff, I think that makes like a curve or something, right? There's some sort of like weird like curve that you can get out of it, right? Influences found a quote think of Vladimir Arnold. He was a Russian Soviet mathematician. He worked on the CAM theorem. CAM theorem? What's that? Mathematician is the part of physics where experiments are cheap. Mathematics is the part of physics where experiments are cheap. Yeah, fair enough. Math is cheap. Math is just very cheap.
Arnold's derivation of Snell's law and how he used it to infer the properties of the rainbow.
So he's the
And
Arnold
some
part
other
of the
stuff,
Arnold
which for now
theorem.
remain a surprise.
That's cool.
You might already know how to derive Snell's law, maybe even in several different ways. But I assure you, few are as elegant as Arnold's.
As elegant as
There is
Arnold.
one last thing that I want to say before we move on. Like most beautiful mathematics, Arnold's argument is very subtle and quite nuanced. So don't get discouraged.
A
if you
randomized
find yourself
dragon
a bit
curve?
lost in the details. You can always work them out for yourself at your own pace or accept them at face value. Whatever works for you.
I think it's using the visual as like a, it gets crazy.
There are many ways to enjoy math.
No way. Where's Gauss when I need him? Gauss!
Arnold's essays
I need
are written
optics.
for readers with a level of maturity that is probably far less common among amateur mathematicians than Arnold might have hoped. In particular, he assumes the reader already
an
knows
AI
of
image?
Snell's law. The purpose of this segment is to bring you up to par,
Gauss.
to present Snell's law in a way that is accessible even if you don't know anything about optics or trigonometry, along with some other useful ideas. that
Well, he
will
said there's no
require later.
AI in the video, right?
If you don't think you have much to benefit from a review of Snell's law, feel free to skip forward. I will not be offended.
Hold on. 8:25, that's where we're at right now. What was it? About AI usage in this video. A lot of people are sensitive about AI. Nowadays, wanted to clarify how I use AI. Oh, okay. Most importantly, none of the concepts, script, editing, narration, mathematical illustrations, diagrams, or animations, music, realistic photographs, and so on are AI generated. The core part of the handcrafted, the core content is handcrafted, and AI is only used for flourish or varnish. Simply put, if it doesn't look AI, it is not AI. I do use AI for the following: upscaling voiceover recordings, generating simple graphics, generating visual fluff for when I'm really stumped about what to put on screen, but my friends insist that leaving it blank would for so long is a little too awkward. A little AI generated visuals used for this video are all generated locally on my GPU using free open source models, mostly SDXL, for image generation and animation. Animation. ZImage Turbo for icon generation, Whisper for subtitle generation, and an NVIDIA broadcast, which is not open source but it's free and local for audio upscaling. So at 8:25, yeah, okay. There's some drama in this Discord about this video in particular. Because I could see like this video, like that's clearly AI. The beach chair reminded you of it. Skirt. I don't see this being the worst case scenario, but like, if you don't need to use it, don't use it. Visual fluff will get you in trouble regardless, right? Why not have generated your own image? Or not generated, drawn your own image. Or visual, or a nice little interesting animation in lieu of that then. Or just like, image of the guy. And then like, I don't know, like there's ways you can replace this without needing it to get into that drama. But I mean, regardless, like it's not the biggest deal in the world. It's just like, yeah, Photoshop, like you must be this tall. It's fine. Because now you're going to scrutinize every single part of your video about what is or is not AI. Huh. I mean, I'm not one to scrutinize that. I can see the use case of some people doing stuff like that, but like, if you're using the images now at that point, like, what's the point? Hi, Lena. Lena Catalina, how's it going? We are watching. Yeah, take a picture of yourself in the background. Yeah, we're watching a video about how the mathematics of rainbows exists and optics and stuff. Right now, we found a part that he might have used AI. Well, he has used AI in this video, but he says, small things. It's like, this is an AI image that he made, which honestly doesn't look bad for what the case is, but like, it's still a little confusing. Why would you use it? So,
in particular, he assumes the reader already knows of Snell's law. The purpose of this segment is to bring you up to par, to present Snell's law in a way that is accessible even if you don't know anything about
What does he say here? I realized in post-production that for some reason my voiceover got a bit modulated at some points in this section. Honestly, I think it sounds kind of cool. Okay.
know anything about optics or trigonometry, along with some other useful ideas.
Anyways, this is like an ode to Vladimir Arnold, so I will hold my tongue as we learn more about the video.
How do you approach finding the fastest route? If you ever took a calculus class, you can probably already guess the answer. But don't worry, I'm not going to assume that you had. We are going to use a method most commonly known today as Rolle's theorem. Though the underlying idea existed for centuries before Newton and Leibniz started to fight over who invented the derivative. Let's see be the point.
Wait, what was that with was that Newton? The Virgin Newton versus the Chad Leibniz. Yeah, Veritasium has a video about the physics of the rainbow. This is more specifically about Vladimir Arnold's description of it. He was the Soviet mathematician. So, pretty important dude, and he wrote a nice book that described it in a very clean way, which is what the creator is referencing. So, we're going through that book.
Let's see be the point where we meet the line of water. For any specific arbitrary choice of C, it's actually quite easy to compute how long it would take to reach B from A through C. The numerical answer depends on how we measure times and distances. But if we cleverly choose our units such that while on ground we run exactly 1 unit of distance per 1 unit of time, then the time it takes to run from A to C is exactly the distance from A to C. We can almost say the same about the time it takes to swim from C to B, except this time we multiply the distance by n.
A constant.
Remember that n is just how slower we are in water. So if, for example, we swim half as fast as we run, we would set n equals 2. Once we have this formula, we can compute the distance for many values of C and see what we get.
Oh, I see.
Next, we plot how long this takes for any given C. And when we do, we notice something interesting. There is a unique optimal choice for C that gives us the fastest route. The key to the method is to note that the optimal point has a unique property. If we look at a point, say, to the left of the optimal point, we find that the graph has a downward trend. Similarly, as we move to the right, we find ourselves in an upward trend. Only at the optimal point, the graph looks like
the arrow's wrong.
It has no upward or downward trend. It's taking an infinitesimal break, catching its breath after the great decline to the left and before the great climb to the right.
He's explaining like the basic calculus of it without saying calculus, which that's kind of nice.
But before we can do that, we need a better formula. Specifying A, B, and C actually contains a lot of superfluous information. We can move A, B, and C in many ways without affecting the solution to the problem, which implies they contain a lot of information we don't actually need. When we think about it, all we really care about is the angle at which the light hits the water, which we call the incidence angle, and the angle it bends to after hitting the surface of the water, which we call the refraction angle. In this video, we call these angles alpha and beta, respectively.
I know this
Snell's law tells us how alpha, beta, and n are related to each other. But before we state it, we need to talk about angles.
Works because of angles, so yeah, that's silly.
What is an angle? You learned in school about degrees, but have you taken the time to think about what they really represent? A nice way to think about it is in terms of arc length. The angle tells us how much.
Yeah, tell us the story about that too, because if you've met Arnold, tell us.
1 degree,
because that sounds really cool.
Exactly 1/360th of the circumference. Or in other words, the arc length over the entire circumference is exactly the number of degrees over 360. We can rearrange this a little bit and recall that we actually know how to compute the circumference. It's just 2 pi times the radius of the circle. With a bit more simplification, we see that the arc length is just the radius times the degrees times this ugly constant. If we decide that instead of 360
Did he call pi ugly?
there are 2 pi degrees,
you say the ugly constant?
This new unit is called a radian, and there are 2 pi radians in a circle. Angles and circles play very nicely together. We can rotate the angle however we want and still get the same arc length. Similarly, an angle that is twice as large gives an arc that is twice as long. This is all nice and well, except light usually doesn't travel in circles, but in straight lines. If we try to directly apply this approach to straight lines, we run into a problem. Moving the angle without changing it causes the projected line to become longer and longer.
Hmm.
To reason about the connections between angles and straight lines, we need a slightly more sophisticated approach.
Isn't it like a
The key is to
cosecant
note
line or
that
something like
the
that?
angle tells us how fast we accumulate distance from the line R as we walk along the
I
line
forgot my
C.
basic trig, but like I
It is
forgot.
not true
Is
that
that's
if we
called
go
like a
with twice as large
cosecant or
angle, we accumulate distance twice as fast.
cotangent or something weird
But
like
it
that,
is
right?
true that this rate is a property of the angle theta and does not depend on R. So this number that tells us how fast we accumulate distance is what interests us. And this number has a name. It's called the sine of the angle.
Oh, it's just a sign that
You
I'm
can think
stupid.
of it as a correction to the angle itself that makes it suitable to work with straight lines. When the angle is 0, we don't accumulate any distance at all. But if alpha is a right angle, we accumulate distance from the white line as fast as we walk.
Hmm.
This shows that the sine of an angle is always between 0 and 1, at least for angles between 0 and 90 degrees, which are the angles we care about in this video.
Okay, so he's
The
kind
last
of.
thing we need to discuss is the notion of approximation.
I see. So he's just t-balling the idea of like some of the trig ideas. So you're gonna get a constant in some sort of like trig way, and then without scaring the audience, you're gonna teach them like some basic fact about it, which is all we need. Also, that's really cool. He say, well, in late 2000s, I was studying in Moscow, and even though I was not in MSU, I sometimes could sneak into the MSU to some seminars. Once after each such seminar, people went to a meeting. I think it was a memorial for 𝖈𝖗𝖊𝖉𝖎𝖙𝖘, and Arnold was there. Really? Yeah, because of the theorem that we were just talking about. That was for the CAM theorem. What does that cover? I'm not as familiar with that, but that sounds like really cool. You were in Moscow? I want to go to Moscow. I want to check out your Russia. That'd be kind of cool. I know there's like what do you call it? There's programs where you can get study abroad and do stuff like that. I wouldn't mind doing that for, let's say, like a semester. That'd be really cool. I would like to try that out.
The approximation we use is usually called linear.
You left
Consider
Moscow a
the
long
right
time
triangle.
ago. No, I get
Let's
that.
draw
I get
an
that
arc
bit.
inside
I'm sure.
Now note
But
the small purple segment. I want to
during the
argue
time
that
while
if
you
the
were
yellow
there,
line
that
is
sounds kind of
short,
cool.
then the purple line is insignificant. It's easy to see that as we make the yellow line shorter, the purple line also becomes shorter. But that's not enough. To truly see what
Oh, yeah, of course.
insignificant means,
Until
let's
it ends, then
assume
we'll.
the yellow line
I
is
wouldn't
a
mind
little
going.
shorter. So it always
But right
takes
now,
the
it's
same
probably
length from our
it's
perspective.
too hot of a time. I wouldn't be
Because
there
of how
anytime soon
zoomed in we
anyway.
are, we place
So
a banana for scale next to the triangle.
no worries.
We see that even though we zoom in, the
got a
purple
banana?
line still grows shorter and shorter. It grows shorter even compared to the yellow line. If we call the yellow line epsilon, then this purple line is what we call little o of epsilon. It roughly means that the purple line is so small compared to epsilon that it doesn't even affect the trend. Let me show you what I mean.
So to talk
If we
about
assume for a
small
second
angle
that the radius is
approximation
1,
stuff right now.
we get that the entire
So,
hypotenuse of the
for small
triangle
angles,
is 1 plus
theta
sine
is
epsilon.
basically
To see what this
theta.
means, let's compare the length 1
or
to the actual
cosine
length of the hypotenuse.
1 minus
I
cosine or
wrote down
whatever
the
the case.
explicit formula, but you don't have to understand it. The entire point is that we didn't have to compute it to begin with. So 1 is a linear approximation of this expression in orange. What does this practically mean? It's easy to see if we plot both our functions on our favorite graphical calculator. The orange function, now in red, is identical to 1 at 0. But more than that, as we zoom in closer and closer, we see that the entire function starts to look like the straight line. The difference between this function and a straight line, the O of epsilon, is too subtle to affect its trend.
I don't know why you would use that visual
Another
then
famous
if you have
example is the
Matt Manham to
so-called
like show that
small
off.
angle approximation.
Just like zoom
For a
in
small
and
value of
show what
alpha,
that looks
the
like.
sine of alpha is approximately alpha, at least when alpha is given in radians. Again, we see that the functions sine of x and x agree on x equals 0. But moreover, as we zoom near 0, the sine function quickly becomes
Yeah, I know
more
this bit. I know
similar
this bit.
to the line y equals x.
I'm gonna fast forward a bit.
And that's all we need to state and prove Snell's law. Recall the constant n.
Basic
It records
trig.
how slower we are in water compared with air. It is not a velocity, it is a ratio of velocities.
That's
If
what's
instead of air
dimensionless.
and water we'd have used some other materials, like glass and oil, then n would have been different. Snell's law tells us that the ratio between the velocities is exactly the same as the ratio between the sines of the incidence and refraction angle.
I remember
n
that.
equals
Okay.
sine alpha over sine beta. If we know any two of the values n alpha or beta, Snell's law tells us the third. To compute n, we only need to measure beta for one value of alpha. Once we know n, we can use Snell's law to compute the angle of refraction for any angle of incidence. N is called the index of refraction, or the coefficient of refraction. Measurements show that for air and water, n is about 4/3. And with that, the stage is set. And we are finally ready to dive into Arnold's derivation of the rainbow.
You once read a whole book about refraction? Then this is going to be some review, hopefully. Get ready. God tier approximations ahead. Chapter 5.
AC. We call the incidence angle alpha, as usual. We want to know what happens to the distance between A and C if we move C just a little bit. So we let D be the point that we get by moving C a distance of epsilon.
Okay.
And try to understand what happens as epsilon approaches 0. We are interested in how longer AD is than AC. So we draw a circle around A through C. The change in length is exactly this little purple segment that is outside the circle. We call the meeting point of AD and the circle C prime. So the change in length is exactly the distance between C prime and D. Arnold's proof uses 2 steps of linear approximation to work out how the change in length behaves for small value of epsilon. The first step is to draw the tangent line to the circle at the point C.
Okay.
This is exactly the line that meets the radius at a right angle. We let E be the meeting point of the line AD and the tangent, splitting the line C tag D into the 2 segments, C tag E and ED.
You have a proportion then?
We want to see what happens to C prime E as epsilon grows smaller. But before that, note that the new angle ECD is actually equal to alpha. This is true because ACE is a right angle. As before, we zoom in at a rate that leaves epsilon fixed. Here is another banana for scale. We clearly see that C prime E is small even compared to epsilon.
Banana for scale.
In other words,
kind of
it
a
is
funny
little
gag.
above epsilon, and it doesn't affect the trend. So our first approximation is to get rid of it and remain with ED. Now Arnold does something a little bit spicy. He extends the line CE until it makes a right angle with D, calling the new vertex E prime. We zoom in as before and find that the distance between E and E prime is also O of epsilon, which means that approximately ED and E prime D are the same. And this makes us happy, because we know that E prime D is just epsilon sine alpha.
Oh, okay.
If we repeat the exact same argument for the part of the path that is inside the water, we find a similar expression, except it has a minus sign and it is scaled by n. You are more than encouraged to verify this for yourself. So for very small values of epsilon, the difference is just epsilon times sine of alpha minus n sine of beta. But remember, the optimal point is exactly the point where the function doesn't want to change. So by equating the total change to 0, we finally get the equation we wanted. We can quotient epsilon out, move the negative part to the right, and divide both sides by the sine of beta. And just like that, we proved Snell's law.
Okay.
But are you ready to see the rainbow?
Is that really that simple? Well, I say simple, but like,
It
I
is
guess
the
that
afternoon of a rainy
makes
day,
sense.
And you are standing with your back to the sun, looking at the sky. What are you going to see? What light will bounce back to you? To answer
Cosmic
that,
rays.
We need to understand where the light comes from and what it hits. The source of the light is, of course, the sun, which is so far away that rays that reach us are practically parallel. Some of these rays will hit tiny droplets in the sky. We assume droplets are perfect balls of water and work out what happens to light rays that hit them. The curvature might be a bit jarring, but zooming in, we see that near the hitting point, the droplet surface is approximately the tangent line. So we can use Snell's law to work out better. Most of the rays will refract after hitting the back of the droplet, and we will never see them. But some of them will reflect off the back of the droplet. To find the reflection angle, we look at the tangent again, and use the fact that the reflection angle is always the same as the incidence angle. When the ray hits the droplet surface for the third and final time, we can simply apply Snell's law again. Before diving into the calculations, let's play with this and see what happens. By increasing the value of n, we see that the angle gets tighter and tighter, which is interesting, but not very relevant to our video. It's far more interesting to see what happens as we move the ray of light up and down. We see that as the ray rises, the angle becomes wider and wider, until suddenly, it starts to narrow back down. Spoiler, this is the reason there is a rainbow. To see why, let's check what happens to a bunch of rays at once. As the rays hit the droplet higher and higher, they hit the ground closer and closer to the horizon. At least until some point. I marked the rays up to this point in red. The remaining rays, still in yellow, actually start to grow farther and farther from the horizon. And it seems that the droplet focuses most of the light into the angle where this reversal happened. We can see a nicer demonstration if instead of drawing a few very bright rays of light, we send many rays which are much less intense. In the spirit of approximation,
I kind of like the
assume all light is
animations
reflected in
here.
this
It's
angle.
not that bad.
I will not see this ray of light. It will hit me in the chest. But my wife, who stands in front of me and is a bit shorter than me, will see it. I will see a different ray that hit a bit higher. And Nacho will see a third ray that hit much lower. The important fact
They did it with
is
the
that we
laser
will
and
all
glass
see the
sphere.
light as
Is that
coming
right?
from the same angle. To make this into a rainbow, we need another fact. That the index of refraction of light in water actually depends on the color of the light. Higher frequencies, which corresponds to colder shades, are slightly faster in water than warmer shades. The warmer the shade, the faster the light. The extremely oversimplified explanation for this phenomenon is that light with a higher frequency has more energy, so it interacts more with the water. The true explanation is of course much more nuanced, and there are terrific videos about
Oh, we're
it
not
on
getting
YouTube
into that.
already.
We're not going to get into any of that.
This phenomenon, known as diffraction,
That's kind of cool that there
explains
is
how
like
prisms
another
work.
source to watch that
They
though. I
portray the
appreciate that.
phenomenon in a very exaggerated way, and it actually looks more like this. The ray might seem wide, but as it traverses the distance back to the ground, the separation increases. Let's exaggerate it again for the sake of explanation, and ask ourselves what Nacho sees. It's tempting to think that the gradient we see is the rainbow, but that's not quite the case, and the strongest indication is that this rainbow seems upside down. Let's think about this a bit more carefully. Of all these colored rays, Nacho will see exactly one. If we consider a different ray that hit, say, higher, Nacho will see a different color. Other rays will miss Nacho entirely. To understand what Nacho sees, we need to consider all of the rays. We start with a low ray and see what happens as we make it higher and higher. As it sweeps up across the sky, we see that it is actually the cold tones that Nacho sees lower. Let's see this again with many more rays.
Okay.
This already provides us with a very nice qualitative understanding of the rainbow. But how do we actually find the angle? We can measure it with a protractor and find that it's about 42 degrees. But that's definitely not good enough for Arnold. Let's see what he had in mind. We already computed the angle at which the ray of light bends at each bounce. We want to use it to find the angle from which the light hits us. We call this angle theta, but it will actually be more comfortable to mark down the angle theta over 2. Because now we can consider
Some basic
the radius that
unit
is
circle
parallel to the ground.
trigonometry.
And notice that it makes the same theta over 2 angle.
I'm
This
bad at.
follows from the zero.
Oh, I forgot my basic geometry right now.
We can now look
forgetting
at the
quite a
other
lot.
ground parallel radius and note that it creates an angle of alpha, this time according to the F rule. We also name the angle between these two angles gamma. We now
Gamma.
recall two very basic facts. There are 180 degrees in a triangle, and there are also 180 degrees in a half circle.
I just realized the
We're
reason why he's
comparing the
explaining it like
equations
this to
with
people is
and
probably
and
because
slightly rearranged.
atmospheric
Find the
science
expression for
and stuff like
theta
that,
in terms of alpha and beta.
uh,
But we are not done yet.
you don't
We
need to
want
be like
understand theta
the
as
most
a function
intense in
of how high
calculus
the ray
or
hits the
any other
droplet,
these subjects.
which we just call age. But it's easy to see that
So
age is
it's
just the sign of alpha.
very intuitive.
This gives us alpha in terms of age, and Snell's law gives us beta in terms of alpha.
I have a friend
You're
that does
welcome to do
atmospheric
the
science,
messy
so she was showing me like
calculation
the math
But
homework
the
that she
upshot
got.
is this
And
function.
she was showing like Rayleigh scattering, and I was like, wow,
I
that's
know
cool.
not many of you will find this equation easy on the eyes, but you should be more forgiving.
As a geometer,
It
it makes
encapsulates the
sense.
entire complexity of a ray of light traveling through a ball of water.
Wait, what do you do as a geometer
This
then?
makes it very useful to us. If we know at what height a ray of light hits the droplet, the formula tells us the angle at which it will reflect. It's convenient to define the height as the distance from the ray that goes through the droplet's center, which we called age.
Okay.
We can also plot how age affects theta, and see again how the angle increases until it suddenly starts to decline. The point at the top is exactly where the rays change their direction. Let's call it the angle of reversal. The graph tells us how the light gets focused. Let's consider the range of about 5 degrees next to the angle of reversal, the angles between the two perpendicular purple lines in the graph. Rays that hit at a height within the orange strip will reflect in an angle at most 5 degrees away from the angle of reversal. Let's now compare it to another range of 5 degrees, this time not close to the angle of reversal. The strip that we find is much narrower. So even though we took 2 ranges of 5 degrees, a lot less light hits in the region that is further from the angle of reversal, and most of the light gets concentrated near it. But how do we actually find this angle? We can use a numerical method like Newton-Raphson, or we can just plot it and use the mouse looks close enough approximation method.
Bruh.
This turns out to be around 0.73 radians, which is about 42 degrees again. If we are truly diligent, we can compute the angle using Rolle's theorem. This actually solves the problem at once for all possible values of
Yeah,
n.
just solve it
But
for
our
0.
purpose, that's
Okay.
completely unnecessary. I put the computation on screen for anyone who wants to follow along. Either way, this is a great point to lay back and admire all of the work that we have done.
That's pretty cool. Yeah. I appreciate the math
Before
shown
we get
there.
to see the full rainbow, there is one last step. A step that Arnold actually left to the reader. Imagine the sky. After a rainy day, even if it looks clear, it is actually packed with microscopic blobs of water. We computed the effect these droplets have on sunlight, but only for droplets that are straight in front of us. So it actually only explains a very narrow strip of rainbow. But there is nothing special about this angle. Due to its rotational symmetry, this problem looks the same from all directions. And when we fan them out, we finally get to see Vladimir Arnold's rainbow.
Oh. Wow. It's a rainbow. That's cool.
If you spent enough time looking at rainbows, you might have noticed something peculiar. The rainbow seems to be lit from below, but dark from above. We can explain this quite easily by slightly extending Arnold's argument. Recall how we discarded all of the ambient light, and only considered the angle where the light is most concentrated. If we hadn't
That's not gonna
done
explain the second rainbow. I'm gonna
reflection
guess
of
it's
each
something
ray
to do
would
with
look
like
something like this.
even more lensing
The glow
following
is
behind
above
it,
the
and it happens to match up another
But since the ray
sequence.
sweeps
I
much
wouldn't
of
know.
field of view, it gets inverted as before. Switching to a front view, we now see this glow under the rainbow. And when we fan it out, we meet Arnold's rainbow again. This time
Wow.
with a glorious underglow. And if you enjoy this exercise, I challenge you to use a similar argument to explain this insane picture taken by my mother-in-law.
The lensing.
Thank you for watching my video. I hope you enjoyed it. If you like to see more videos, then the best thing you can do to help me is to like and subscribe. But since this is my first video,
I liked it.
I don't want to just ask you to subscribe. I want to tell you why I think you should. While I scroll down a list of my favorite upcoming ideas, and I have tons of ideas. About 2 years ago, I finished a PhD in quantum cryptography, which was fascinating. I studied something
Quantum
called unclonable
cryptography. I am nowhere
I also
near
dealt with some other forms of
PhD level at all
cryptography
yet.
and quantum
I'm
computation
always
in
impressed
general.
when people like just do
Before
this and
that,
drop
I
like a
completed
banger video.
master's degree in a field of mathematical logic that is called model theory.
This is pretty good, but my only issue is like why don't we just some of the my notes is that like if you had to disclaim in the beginning that you had like AI being used in the video, that's gonna scrutinize and people have opinions about that. So just don't use the AI bits in the video. Like if you're using it for like production stuff, like filtering out your voice or whatever the case, like no, there's you can disclaim that, but there's a few like filler moments in here that like didn't need any AI at all, any AI like images at all, like the chair or whatever that was in the beginning, right? It was like you have the chair, yeah. Like why not just use a clip art for this? When am I becoming PhD level? Give me a few years. I will be there. This guy could pass Pythagoras for all I know. Yeah, this guy probably is like related to Pythagorean. Look at him.
Studying and absorbing. It wasn't the most productive for my research. Throughout the last 2 decades or so, I came across a lot of beautiful stuff that I want to share. There is such a treasure of beautiful, accessible math that nobody told you about before. And this is my attempt to bring to light and share with you.
Yeah,
all
no,
the
the math
beautiful
is
things
cool.
that I've
The math
seen.
is fine.
And the only way
You
to
explained
do
it in a
is
very
with your
simple,
support.
relatively
So
simple
if
way,
any
and
of
you
these
followed the
things of
proofs and stuff like that. The visuals
then
are really
it
what
will
I
also
liked about
benefit
it. So, what about all this though? In the end over here, empty space.
Congratulations for making it this far. I am
Oh yeah, he had
truly
like a Easter egg or something, right?
As a token of my appreciation, I want to show you something cool. Consider the sky.
The Moraga.
We already know it's filled with droplets. But over a hot desert, they are not uniform. The heat from the ground makes them float upwards. But as they ascend the altitudes, they chill and fall back down. This creates a layer where the humidity is much more concentrated. Using the theory of differential equations, we can show that the trajectory of each ray of light must oscillate about this layer. There are many different possible trajectories depending on the exact conditions.
Sure.
And an important theorem called Picard's uniqueness theorem tells us that two rays of light that emanate from the same source in different angles will never meet. However, two rays of light that emanate from different sources might meet, along with all of the rays between them. Consider an observer watching from this meeting point, and say that the two drawn rays emanate from the top and bottom of some object.
Never used the word
By
caustic,
the
yeah, I
time the light
know.
emitted by the object
Crazy.
reaches the observer's field of view, it is completely distorted, and seems to be at a completely different direction and distance than it truly is. After the meeting point, the rays of light reverse their orientation. And by the time the light from the object reaches the observer, it doesn't only look distorted, but also upside down. This is the simplest form of a phenomenon known as a mirage. More
Mirage.
complicated versions are called superior mirages and include the famous Fata Morgana.
That's pretty gnarly. I like that. I liked it. It was fine. Pretty cool. I will say some scrutiny about the AI, and I cannot let that go. But overall, the video itself was pretty chill. Good people don't promote AI. Hashtag propaganda. Ridiculous. I would say generously, this taught me something. This taught me something pretty cool. Yeah, at least they're stating that they're using it rather than hiding it. But I agree. A lot of the stuff that they're using AI for very easily could have been done with standard art. Like the art, like it's not impossible to find art. Like I'm a VTuber. I find plenty of art that I cannot genuinely use. I'm sorry. I find plenty of art that like there's sources for that. So that just opens you up for some stuff. I will give this though generously 7.3. 7. So like 7, I would say anything that's like. Oh, let me bring my music back too. I would say for most cases, this video would have been fine, perfectly fine. Some of the weird like scripting and production stuff, I feel like he also could have like fixed that out and ironed that out, because I know we had the deadline of like the SoME, and it looks like he produced this 2 weeks ago. What exact date? August 6th. He had like another week to re-edit some stuff, so I don't see how you couldn't have produced this video a little bit faster. You know, there's some of the tweaks that you could have made. I did learn something though. I did learn something. So how would I phrase this? I would I know making videos is hard, but like if it's a recording, then you can like snip out the recording, and then if your edit literally says you know what I'm saying? If you're saying slower or faster, and then you meant to say up instead of down, can't you just snip that little portion and say the word up? I mean, maybe it doesn't sound perfect, but then like just replace just that bit of the recording. It's a small thing in the editing. It's not the worst. And I know catches like that, so like the effort it takes to edit in your reading mistake is probably just, you could have just reset it. You could have just re-recorded it. And I mean, I wouldn't mind one, but there's like probably a few in here. There was like notably like, I want to say like 4 or 5 of that in the video. So I get that. Well, actually, only like 2 of them were like audio. And then like a few were like arrows from Manim and other things like that. But I mean, those are small things that like add up. So I'm like, I'm supposed to be listening to this and then still like understand it. But overall, I think it definitely taught me something. The reveal at the end didn't lose any value. I think that was pretty interesting how we got to that point. The derivation, I could say, is a little trig intensive, right? Because this is supposed to be teaching people that don't know about calculus. So yeah, minimization problems, thinking about angles and trigonometry. The approximations are not the worst, but I think there's a better way you could have explained this without it sounding weird. Snell's law is okay. So we get all this context about like Snell's law, and then we eventually get to the really complicated rainbow part. You know, that's exactly right. That's exactly what you should do. So yeah, no, I'm okay with that. There's plenty of visuals. I think it made sense. So yeah, I would say 7.35. I'll say that. Yeah, overall a great video that taught me something new about I wouldn't say this is not atmospheric science, right? This is about rainbows. Very cool. I do think there's some points to make known. One, if you have AI images used, why not have changed them to non-AI images if overall it doesn't affect the video / delivery? That opens yourself up to some scrutiny and not that opens up yourself up to some scrutiny and perturbs what do you say, viewers about the rest of the video. Two, I would say small script errors / animation mistakes, but honestly not bad. And then like the premise of the video was just fine. I really liked the ode. I really liked getting into this guy. And it comes from a book, so I guess that's where we're coming from. So it was sort of kind of nice. Yeah, that's how I feel. If you're making a video that's, let's say, the mathematics of generative AI, then obviously use AI images as examples. But for something like this, it's completely unnecessary. Yeah, it distracts you because everything else is very well put together. The majority of the video, I wouldn't even say this picture is probably I think this picture is probably AI as well, right? Because this is Fermat, right? Why not have just done? And then I think a few of these other visuals as well. Like they don't harm the video, but in the beginning most of the video looks like it's very clean without it, and then again, that's just the most irrelevant thing, but it's just people notice that and they think that everything about it. Like look at this, Snell's law. I think pretty sure this is like a generated image as well. Right? It looks nice, sure, but I just still don't enjoy that. I don't enjoy seeing stuff like that because it adds nothing. You can keep the clean visuals. You can use primary sources, and if that's something I got scrutinized in school for, then absolutely I'm going to do that. Yeah, just keep away from sources like that if you can. So yeah. Also, hello. Is it Kiwi and Dippy? Is that Adive, but like on YouTube? I don't even know. So I would say this one's pretty okay. The small errors and animation mistakes, honestly not bad. Just clean them up. If you had time to clean them up, then that's not an issue. Then that would been fine. Then I want to say the mathematics was not too difficult, but for kind of the audience, what was this art targeted towards? High school, undergrad, grad, middle school. So yeah, kind of like the scope of everybody, without getting into the intense mathematics. You don't have to say we have to do calculus to solve for these zeros. You don't have to say that we're using these fancy tricks that everyone should know. You kind of built it all up and then you get into it. But that got a little much. But I think that's fine. I think you built up the necessary mathematics used in the video without okay. You built up the necessary mathematics used in the video. However, some would say it covered essentially. No, I don't want to say anything bad about that. Which took a while, but serves its point to audiences that aren't familiar with calculus and trigonometry. It's fine. I liked it. It's fine. I don't know what else to say about that. It wasn't hard to work with, to watch through, if you're familiar, as the visuals provided even better context, or even better reason to how it works. I mean, yeah, the visuals were fantastic. Visuals were fantastic. The animations. And definitely were required to cover this subject in a broad audience. Very nice. Yeah, I just have good impression overall. I had a good with this video. However, I would still avoid using resources that would come across as tacky or showing that this is, I mean, I don't want to say it like that. How do I say this? Just using AI shows me in the beginning that I thought there was going to be more AI in the video, and it turns out there wasn't. However, an audience is going to be influenced by the use of AI for this video, which is still something that wasn't as necessary to use. Yeah, other than the video production stuff, like just don't use those images. You are clearly very well adept in video making, so avoiding them would have been better. Yeah, I don't get why people, like, I mean, to be fair, I would draw or I would put together a thumbnail myself if I was to like do something like that. Like the thumbnails I've been making for SoME have been stuff that I've been making myself, right? Or every single video I go live with, I've been making thumbnails for. So that's just me putting art together because I know what I can do. But some people, let's say, if they don't know how to present a video, then they would probably resort to like an AI source, in which case I'm not sure how. If you're willing to use some of that stuff, then I'm not sure if I'm gonna want to watch some of your content, because I'm not sure how you're filtering out your data, how you're using it. Because I would use AI for, let's say, like some incredibly difficult like coding or LaTeX, just annoying stuff. And even now, like even Manum can be really good at helping you code videos, which that's another problem in and of itself. But like just using them for small things like AI images, like I'm not even sure like how much of this video is like original then. So, but I mean, clearly it comes from something, which is the book that we're talking about. But I'm still like, I'm still perturbed. So yeah, I think that's fine. 7.35 is fine. I liked it. I will submit that about right now. I just wish people wouldn't use it. I don't think that's necessary to use it anymore. I don't like it. Okay. So we still have another 40 minutes before the next session, right? I believe the next session scheduled, that's gonna be oh no, I don't think there's anyone else for today. Yeah, I didn't realize there's no one else for today. Shoot. Then I'll probably just finish off by the 3 p.m. mark, and then I'm gonna have to wrap up because I'm getting tired. So quick little break. I'm a little tired. Let me also look into ahead and see what else is going on right now. Let's see. Or yeah, no, I'm gonna take a quick break. Get up, stretch, redeem. Thanks for the hydrate. You could throw things at me, but I'm gonna take a quick stretch and then keep going. I'm gonna keep going, but I'm curious. So we have what makes a number system, or we have the can you untangle it? Well, you can't untangle, you're not mathematically. I think I saw this video. Some of us covered this one already. I haven't seen this one, so let me take a quick break and then I'll stretch. All right. While we're here, like, what else is everyone doing today? Like, what's the crazy thing everyone's doing right now? Is everyone doing homework? Is everyone, like, doing school or whatever the case is? What's the deal? You want to watch Untangle It? Okay. After this, I think I will be hanging out with Grandma. That's very comfy. Oh, sweetie. Have some cookies while you're here. I'm probably going to be doing some... I haven't made my schedule for this week, so I'm going to probably work on that. Take a nice little break. We kind of finished up breakfast. It's a little late for that, isn't it? I think you're on my time... Or not my time zone kind of thing. I'm not sure how I feel about this. Pen, you're funny. Ha 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 ha. Ha ha ha. Not too late for breakfast. You're just on your way to work? Tyler, enjoy your day. Do not get too stressed about work. I know how it feels. I mean, it's a very comfortable time for the day for that, but still. Let's see, after this, I'm probably gonna go and get some more food. I kind of like... Am I in a Jack in Box kind of mood today? I don't know. Yeah, Tyler, you work hard. You work very hard. Go enjoy a comfortable day for that. Yeah, I gotta make my schedule, my Vtuber schedule. I gotta show what we're doing today. Also, since you're here, I can share off a quick little something with everyone. I'm gonna get a new... I'm gonna be getting a new... I'm working on a new loading screen. So for when streams start, I'm gonna have a little, like, nice little animation playing in front of it.
while we wait for me to actually like start the stream up. So getting started stream, that's what it is. I'm gonna be getting a new one because the current one that I have is something that I made, and then the outro is one that my animator made. So I'm gonna be working on a new one. It's gonna be animated in 2D with my artist. It's gonna be very nice. So like a typical like VTuber introduction video, you know, while we wait, and then I can actually do the things I'm supposed to be doing. So I can run the stream and then have you guys watch it, and I can actually be late while still live. Yeah, that's the plan. And then tons of other art projects, tons of other 3D things that I'm going to be doing. I think I have time this week to actually do it, so I think I still got to work on Millennium's thing, her animation stuff, and then I also still have studying to do this week. So look forward to that. Absolutely look forward to that. And then we'll be working on that. Hi Terry, Terrified Games from Twitch.tv/Terrified Games. Everyone check him out. He plays video games sometimes. Terry. Check him out. He's cool. Everyone follow him. Let me go. Also, my cats want to leave. My kitty cats. They're stuck in my room. Hi kitties. Hi Lawrence. Hi Phillips. I want to let you free. Let's go. Let's do this thing. Go. You're free. You're free. Go. Oh, there we go. Okay. Also, one other thing. You haven't sent pictures? I don't like sharing stuff. I hardly talk on my own Discord server. What do you think I do? I probably should though. I don't like sharing a whole lot of stuff about myself. But yeah, I do have my cats. I love my cats. They're amazing. So I got Baylor, Toby, and Lawrence. They're literal people names. I don't like the whole like, oh my gosh, that's my kitty cat, and then I like spoil them to like oblivion. My cats, they're kind of mid. They like me, but they don't like me. They're just like meh. So, like they're very nice. They're very pleasant. It's just like they don't love me. You know, does that make sense? So I don't get to have like too much like one-on-one time with them. I used to have enough free time that I just go around to them and be like, oh my gosh, hello kitties, and then like spoil them. But yeah, I do hate the whole fur baby thing. Yeah, this is my fur baby. This is my fur baby. Let me go spoil him. This is my pit bull. We're gonna have him around the crib tonight. His name is Princess, or her name is Princess. And then like, you know, just my mom worked at a children's hospital, so there's quite a lot of stuff. Well, I mean, it goes for like any pet, I suppose, but like the fur baby, yeah. My dog deserves a spoiled. I need a chicken bowl for my dog. Let me bring a pit bull by the name of Princess to a 2-year-old's birthday party. All right, take a picture. You judge people based on how many nicknames they have for their pets. Yeah, right. His name is Princess. He's me forever. So okay, yeah, Pen, you're right. Because my cat Toby, right? Okay, Toby. I can agree. Just short for Toby, it'd be like Tobes, right? Tobes. That's fine, right? Lawrence. Technically a short name for Lawrence is Larry. We don't call him Larry. We just call him full name Lawrence. Baylor, we just don't call her anything else. We have her just called Baylor. We don't say or Bebe or whatever, but like it's I just treat them like straight up like people, kind of, you know. I call my sister's cat by his name, and I call it like a rat. He's a sphinx. He's a rat. Rats. We're the rats. Ain't nobody gonna mess with that. Rats. Anybody get that? That's a German reference. Anybody? No? Anybody? Okay. Also, I do want to show some really cool thing too. I was going through my old VODs on YouTube, and I was putting what do you call it? I was putting thumbnails to them all. So all my old VODs, I can actually share off what I actually did from that session. And then I still have a bunch of like actual streams that are not listed. So I'm gonna make a VODs channel at some point and then show that off. But the one of the dumb videos that I ended up making an art for is this one. It's so stupid. if that doesn't take up all my space. So I was covering like Dedekind and Cantor, and I was like, oh, that'd be really funny if I made a thumbnail like this. So, just like the story goes that Cantor kind of threw Dedekind under the bus to get in touch with the German academia. So I made the entire thumbnail, this entire meme by myself. And then I kind of wanted the picture of Chroniker to just be like giving him to flip him off. I thought that'd be really funny. So yeah, that's without my face there. That's the meme is just literally friendship ended with Dedekind. Chroniker is now my best friend. Yeah, he threw Dedekind under the bus. And by the way, Dedekind cuts. We just covered that video, right? And then Cantor also just got made fun of in the end by everyone because he started like talking about infinities, and turns out infinity is a very unpopular subject amongst Chroniker and all the other German mathematicians at the time. Sucks. Also, one other thing I will say, I'm tempted to do this week, but I'm hoping I kind of don't want to because of other production stuff, especially Chroniker. Yeah, that was the point. So I thought that was a really funny time when I covered that article. It's really good. And there's another stream I will be doing in the not so far future. It's this one. Yes, I want to open this one. Autosave document, please. This is me stalling kind of before I go finish the last video, and then he's such a big streamer, guys. I don't know about that. But the next stream I'm really interested in doing, it's gonna be about this actually. So, I really want to do date math. If you guys are familiar with date math, are you gonna crash the party tomorrow with Amy? I could totally do that. I think I work tomorrow. But I'll see what time I'm available and how that works. Are we doing morning session? Oh no, yeah, I work at that time. I'm sorry. 3 to 5, my time. I'm unfortunately unavailable at that minute. Sucks. Maybe next time though. I think there's some more sessions we could definitely do this week, especially the VOD stuff. But yeah, there's a game out there. It's called Date Math. So you get to date mathematical concepts, and I want to play it. I wanted to interview the person that actually made the game, so that's what I was gonna do. But I haven't been able to contact them. So until then, I might actually just straight up play the game. So this is available on itch. It's like right there. It's available, and I really want to play it. So that, and then look forward to some other streams in the future. It's all math related stuff. I have tons of things I'm gonna do. So look forward to that. I tangled up at work and not going to make it. Did you really just say not? I know. Okay, I've been stalling a bit, but I just wanted to share that I'm very excited for the future about some stuff. So I got some streams. I got this one. I have another one. It's called Proof. It's a Broadway, not a Broadway show, but it's a play. Tons of other things, tons of stuff. So look forward to that. I do streams on occasion. I have an ad coming up in 3 minutes. I may as well just like get this one going. Okay, I think we did like 4 so far. This will be the last one, and then I'm gonna go and get like a Jack in the Box. I'm gonna Jack in the Box burger with my money. So yeah, let's go ahead and get into that. It says here, why you can't untangle your knot mathematically. High school, undergraduate level, knot theory, knot invariance, and then link invariance. That is a very simple topic. Children learn this topic quite often. In fact, one cool thing I'm going to show off. Actually, I should probably show that off while I prep this up. There's a bunch of presets in Blender about like knots, and yeah, I should show that. So while we watch this one, I'm going to pull up Blender and then I'll show you something kind of cool. But I think I remember seeing this one, right? No, I was about to watch this one. I don't know anything about it. Take a rope. Alright. Let's go ahead and watch this one. Pen, are you ready? Are you not ready for this?
Are you not ready? Get it? Are you not? Are you not ready? Are you not? Okay. Let's go ahead and watch this one.
Tangle it up.
Take a rope.
Take a rope. Tangle it up, and then fasten the two ends together. You've formed what mathematicians call a knot. Technically, we should imagine this rope has no width, so the knot is a one-dimensional object.
Oh, okay.
Without doing any cutting or passing the rope through itself, this knot can be untangled to look like a circle, otherwise known as the unknot.
This is another knot. Unlike the last one,
That's the
I'm
one
not
link.
able to easily untie it. But how could I know for sure that untying it is impossible? I could mess around with it for hours and never get it untied.
Stop roping
but that would only
me
be
into
evidence,
this dude.
not proof. Is there a way for me to prove once and for all that untying it is impossible?
You take a bottle. It becomes a glass. Where did it go? It's in my...
We consider two knots to be the same if one can be transformed to look exactly like the other without cutting the rope. Thus, the question, can we untie this knot, is the same as the question, is this knot the unknot? This is a specific instance of the much more general question, are any two given knots the same?
They're all variant.
So our real goal is finding some way to prove that two given knots are not the same. To generalize the problem further, we'll introduce the concept of a link. A link is basically the same as a knot,
Nice.
except you can use more than one rope. Take any number of ropes, tangle them up as much as you like, and then fasten the free ends together until there's no more free ends. The result is called a link.
No scissors
Two
allowed.
links are the same if one can be transformed to look exactly like the other without cutting any of the ropes. The question we'll focus on in this video is, how can we prove that two given links are distinct?
This is a hard problem. There are a continuum of decisions one can make in how to deform a piece of rope.
Okay, so real quick, I want to say the most knot theory context that I genuinely have, I took an REU, and it was both taught either in in differential geometry or knot theory. So we had the option to do either one, but exclusively one. Exclusive or. So we were, what do you call it? Oh yeah, sorry about the ad. We had the choice between knot theory and differential geometry. I got the basics of knot theory, and there's a really cool program that came with it. It was letting you do, what do you call it? You can describe your knot and the connections and links that you had, and follow through with untangling it. So you can find out when things, I guess, phase through each other and what things don't. And by the way, I kind of dig knot theory. If you guys look over at my shoes, these are knots as well. I had that as part of my design. Those are like 10-fold knottiness or something like that. As to what that actually means, I do not know because I am not a knot theorist. I just happen to kind of like math. So that's cool. It's fine. It's fine. I'm not the best at knot theory, but when we get there, I don't mind it. It's kind of like a topology kind of class, but also kind of like number theories and different things. It's like a very menial kind of mathematics that's fine to just keep up with. It was not a website. It was actually like a package, like a C++ package, a very a very low, like under the table kind of like program that not everyone got to use. It's really weird. Anyways, let's continue on. Sorry about that.
I could cross this piece over here, twist this
Alexander
end,
has entered the chat.
deform this
Hello.
and slide this part through, and infinitely many other things I could do to try and make this link look exactly like the other. These changes are called ambient isotopies of the link. I could be sitting here for 10 days straight, trying different ambient isotopies before I finally get it. The proof
Isotopies.
that the two links are different somehow has to rule out all infinitely many possibilities.
Yeah, no, it's like
Sounds
it's
like
a
formidable
it's a
task,
downloadable
but there's
program.
a common strategy that's useful in these situations. The idea is to construct an invariant, a value you can compute from a picture of a link that doesn't change no matter what ambient
But it's something that you had to install on your own.
If we're able to find an invariant that's easy to compute, and the two links in question are assigned different values under the invariant, then they must be different. For instance, there's a very simple invariant associated with a link called the number of components. That's just the number of distinct ropes used.
Okay.
This link has 2 components, and this link has 1 component. No ambient isotopy can change the number of components, so the links are certainly distinct. However, this invariant isn't particularly powerful, because there are lots of different links with the same number of components, and this invariant can't distinguish them. In particular, if we want to be able to distinguish two knots, which are just links with one component,
You just
we're
find out
going to
the
need a stronger invariant.
intersection points, right?
There's a continuum of different ambient isotopies that
So
can
check
be
out the
performed
cover
on a
art.
link, and whatever new
do that later.
invariant we devise must be unchanged under all of them. Luckily for us, most of these isotopies are very similar. The result of this one looks more or less the same as the result of this one, which looks more or less the same as the result of this one. However, these two look more distinguishable, particularly because the pattern of rope crossings is different. In other words, in order to make one of these pictures look like the other, you have to slide the rope over or under itself. Two pictures that can be transformed into each other without changing the pattern of crossings are visually similar, and such a transformation has a name. It's called a planar isotopy, to emphasize the fact that the changes to the picture are happening in the plane rather than in the ambient three-dimensional space, which tracks the crossing information. All planar isotopies are ambient isotopies, but not vice versa. If we cooked up a quantity associated to a picture of a link that's computed solely from the link's pattern of crossings, then that quantity would automatically be invariant under planar isotopies. That's because two pictures that differ only by a planar isotopy, like these two, have the same pattern of crossings, and thus the quantity associated to each of them would be computed in the same way. So whatever invariant we develop, we'd like to be able to compute it from the link's crossing pattern.
Here's an example of a simple quantity called the linking number. It won't be able to distinguish two different knots, but it does fit our criteria of a number easily computable solely from the link's pattern of crossings. Take a picture of a link and assign an orientation to each component. That's just a consistent choice of direction along each rope, which we mark with arrows. To compute the linking number, take a close look at each crossing. If the overstrand and understrand are both part of the same component, write a 0 next to the crossing. Otherwise, consider what happens when the overstrand is rotated counterclockwise to be parallel with the understrand. If the arrows point in the same direction, write a 1 next to the crossing.
What?
On the other hand, if the arrows point in opposite directions, write a -1. Do this for every crossing,
Yeah.
then add all the numbers together.
That's a weird way of saying
divide
that,
by
but
2.
basically, if you're going over or under, I believe that's like the direction, right? So then if you have an over or under direction, and then an over and under and over direction, then something like that would cancel and become numbers and stuff. And then you add them up, right?
You've computed the linking number for this oriented link. Although it's not immediately obvious, the linking number is an oriented link invariant, meaning that as long as you don't change the orientation of the components, any ambient isotopy of the link won't change the linking number.
This is quite a useful result. It tells me that this link, called the hopf link, can never become this link, called the unlink, since the hopf link has a linking number 1 or -1 depending on the chosen orientation, whereas the unlink always has linking number 0. If the two links were the same, there would be a choice of orientations for each that assigns them the same linking number.
That makes sense.
We skipped the proof that the linking number is actually unchanged under ambient isotopy. We'll come back to that later. But it should at least be clear that the linking number is unchanged under planar isotopy, because it's computed solely from the pattern of crossings, and any two link pictures related by planar isotopy have the same pattern of crossings. Unfortunately, the linking number of a knot is always 0, since the overstrand and understrand of every crossing are part of the same component. Thus, we can't distinguish two knots by their linking numbers.
There's a slight issue with how he presented the linking number, which you might have noticed. We assumed that every crossing was very simple. One rope, called the overstrand, passing over another rope, called the understrand, at a single point.
Over and under.
This assumption was necessary in order to cleanly define the linking number, but in general, the crossings in an arbitrary picture of a link might not be so straightforward. For instance, one strand could touch another strand at a single point, like this, with either a cusp or a point of tangency. Or 3 or more ropes might cross on top of each other. Or 2 rope sections might be parallel and stacked on top of each other. In these scenarios, it's not exactly clear what counts as a crossing, what the overstrand and understrand are, and how to compute the linking number.
That's why you have to
clearly
show
define the
you
linking
can
number,
transform it.
We need to resolve these issues by ensuring that every crossing in the picture is simple. In fact, to clearly define any sort of invariant in terms of crossings, we need to ensure each crossing is simple. We'll do that by taking a link with problematic crossings and slightly adjusting it so that all the crossings become simple. First, to fix the situation with the cusp, we need to ensure that the path of the rope is differentiable. Smooth the rope out so there are no sharp points. We also need to make sure that there aren't any sections of the rope that are directly vertical, since when viewed from above, a vertical bit of rope can look like a cusp. Next, to avoid this situation with the point of tangency, we can just move the rope a tiny bit so that there's no intersection or there are two different intersections. This ensures that whenever a crossing occurs, if we look at the tangent vectors of the two strands, they aren't parallel.
Okay.
Finally, to avoid 3 or more ropes crossing at a single point, we just shift each one slightly so that we end up with a bunch of crossings with only 2 strands involved.
Yeah, you gotta move it.
These 3 conditions imply that at every crossing, there is a single overstrand and a single understrand, and the tangent vectors of these 2 strands are not parallel, so they form a simple crossing. A picture of a link that satisfies these conditions is called a generic link diagram, and we can easily compute the linking number of an oriented link from such a diagram.
In summary, we've seen that if we want to devise a new link invariant, we need a quantity that's invariant under ambient isotopy. Such a quantity certainly must be invariant under planar isotopy, so we want to define it solely in terms of the link's pattern of crossings. To do this, we need simple crossings, which occur when we're working with a generic link diagram. But being invariant under planar isotopy isn't enough. We need a quantity that's invariant under all ambient isotopies, which can change the pattern of crossings. Thus, we should consider what kinds of changes to the crossing pattern can occur when an ambient isotopy is performed. It might seem complicated, but it turns out that all the crossing changes that can occur can be broken down into a combination of 3 simple kinds of changes called 𝖈𝖗𝖊𝖉𝖎𝖙𝖘 moves. To see where the 𝖈𝖗𝖊𝖉𝖎𝖙𝖘 moves come from, I'll start moving this link around. Notice that most of the time, the crossing pattern isn't changing. In other words, I'm applying a planar isotopy. However, there are certain isolated instances where new crossings emerge, old crossings are eliminated, or the pattern of crossings changes in some other way. For instance, when I give this strand a twist, a new crossing is generated at this single instant. Or, if I slide this strand over here, 2 crossings are eliminated right now. I could also move a strand like this, causing the pattern of crossings along this rope to go from under-over to over-under, and the change occurs exactly at this moment. Now here's the critical observation. Changes to the crossing pattern only occur when the link diagram isn't generic. If we alter the link in such a way that it stays generic during the entire process, then all we've done is a planar isotopy, and we haven't changed the pattern of crossings. Recall that there were 3 conditions required to make a link diagram generic. No cusps, and that includes no vertical strands, no intersecting parallel strands, and no crossings with 3 or more ropes involved. To change the pattern of crossings, you must violate one of those 3 conditions. Otherwise, the diagram remains generic and no changes can occur.
The first 𝖈𝖗𝖊𝖉𝖎𝖙𝖘 move, called 𝖈𝖗𝖊𝖉𝖚1, involves a violation of the no cusps or vertical strands criterion. A strand with a cusp can either form a little loop with 1 crossing, or be smoothed out to have no crossings. A similar thing happens if part of a strand is vertical. It can be flattened out to have a single crossing, or flattened out so it has no crossings. 𝖈𝖗𝖊𝖉𝖚1 lets us move between the 2 possibilities, either adding or removing a little loop or twist in part of the rope.
Yeah, so that's where part of like knot theory kind of like doesn't seem appealing to me. Is like, it's kind of like, with respect, the most obvious shit in the world, but at the same time, it's like, obviously there's a lot more mathematics that go into it, and that's the whole point of it being a study. So I can't tell what is like something that is fascinating and something that is very obvious, because the rigor doesn't seem like it's there. I mean, we're always using like literal knots to demonstrate this stuff. So I can't tell whether something is actually like, this is a theorem, because this is actually something very valuable. I understand like the crossings and things like that, but I can't understand when are we actually learning something new in it? Because the basics make sense, but that's always, it always feels like we're in the basics, right?
Involves a violation of the no intersecting parallel strands.
That's just me. That's just me about knot theory in general.
Either by forming 2 simple crossings, like this, or eliminating the intersection, like this.
Like duh, right?
Moves us between the 2 possibilities, sliding.
I missed the beginning of the sentence. Yeah. It's basically like, I just feel like knot theory either is fairly. It comes off to me like it's either very obvious or it isn't, and it seems like I when we move like some of these things, like obviously we're using literal knots, physical knots, right? Physical strings and stuff like that. Like, I know knot theory doesn't delve into only these things, and there's different like kinds of knots where you like intersect themselves in very interesting ways, but the ones we always end up seeing is like literal knots, physical knots. Like, you can untangle them. You're like, yeah. And yeah, that's useful for like protein stuff, but like there's knots that are like intersectable. Like they phase through each other and stuff like that, and it's very interesting. But it seems like almost all the time it's like when we just said like we can move the knot, it's always like the most obvious thing. Like obviously we can move it. Like what part of this shows me that it's like a function, or something about this shows me that it's like a continuum, like the connectedness. And it's just my only gripe with knot theory, and I can't discredit the subject itself, because the way most kids can learn knot theory. The basics of it is that even kids can learn knot theory. I know because I witnessed this during camp this summer, but I just don't find myself very appealed to it. It's not the most fun to me. If that makes sense.
Either adding or removing a little loop or twist in part of
It's
the
like
rope.
duh, like obviously we can like twist it
𝖈𝖗𝖊𝖉𝖎𝖙𝖘
to get rid of some of these
violation
knots.
of the no intersecting parallel strands condition. This situation
But yeah,
can
that's
be
just-
made generic
that's
either by
just-
forming two simple crossings.
Maybe it's just a very elaborate
or
recreational
eliminating
math
intersection,
problem
like this.
that got
𝖈𝖗𝖊𝖉𝖐
its own
moves us
field.
between the two possibilities, sliding a strand over or under another strand to create or eliminate two crossings.
Bro, that looks sus.
Give a kid a rope.
Finally, 𝖈𝖗𝖊𝖉𝖐
Give a kid a rope.
involves
If they can't get rid of
violation
the
condition
knot,
restricting
then it's not
crossings to
possible.
at most two strands. When three strands overlap at a point, we can make a slight adjustment to any one of the three strands to create three simple crossings. 𝖈𝖗𝖊𝖉 lets us move between the different possibilities. In summary, there are three different 𝖈𝖗𝖊𝖉 moves, corresponding to each of the three ways a link diagram can fail to be generic. The 𝖈𝖗𝖊𝖉 moves characterize the ways in which an ambient isotopy can change the pattern of crossings of a generic link diagram. All other changes to a link diagram are attained by planar isotopies.
To get a feel for how the 𝖈𝖗𝖊𝖉 moves work, let's write down a sequence of 𖈈 moves we could use to untangle this unknot. I'll abbreviate the names of the moves as R1, R2, and R3. We start with R3 right here. Then two applications of R2. We adjust things with a planar isotopy and apply R1. After
Wait, sticky what? Yeah, that's very real. I don't have a good sense of how knot theorists actually do, but my impression is that it's serious math cared because knot complements R3 manifolds, and there's something like you can get a simply connected manifold with a fundamentally group Z and knot complement cared originally. Okay, I see. Yeah, okay, so that bit I understand. Like you would have like intersecting topologies or something like that. You would have a literal physical space to work with. And yeah, are they homogeneous? Is that something that we care about? I don't know. But check out this Mobius strip.
another R2 move, we're nearly there. Just three more.
Oh, by the way, one fun fact about this orientability thing. So you understand, everyone knows about like what the orientability of a the Mobius strip is non-orientable, right? If I was to show that with face orientation in graphics, something that is outward facing, or at least in Blender, it's blue. So if I'm in the interior of the object, it's going to be red, blindingly red, right? So that means that shows me that I'm in the inside. This is going to be backward facing cold, back face cold, and then this is front face cold, meaning that if I was to put this in like a video game, the backwards graphics flip. So this side is the actual side that will actually be normal. Okay, so the light will be hitting this way, but on the red side, this is the back face. Depends on how the points are actually drawn. Sorry, completely irrelevant to the video. I'm sorry about that. But so we have depending on the orientability of if it goes clockwise or counterclockwise, then that determines whether it is front facing or back facing polygons. Now for the Mobius strip, the way that this is generated is you take like a piece of paper and then you flip it and then you connect both ends. So the way it actually looks like in 3D is actually like this. So at no point can you find like a spot that doesn't have well, I guess like an angle like this. Think of it's like projected. I forgot something about not being able to see all sides. So yeah, this side obviously, that means this side is back face cold. We go around it,
and then it's still backface cold. But it literally flips it. So just because it's a program, and that's just how these vertices are compiled. So yeah, this side is back front facing, and then the red side is back facing polygons. So to fix this, for the sake of making a thing, I would do a solidify modifier and get rid of it so that I now have like a Mario Kart Mobius strip. And I would print this or something like that. Sorry, that's all I wanted to share. Sorry about that. Mobius strip.
1 moves to untwist and get us back to a circle.
That is not a circle. What are you talking about?
That's a
Close
circle.
enough.
We now have a straightforward understanding of how arbitrary ambient isotopies can change a picture of a link. Every ambient isotopy can be thought of as a sequence
sense,
of
right?
𝖈𝖗𝖊𝖉𝖎𝖙𝖐 moves, interspersed with planar isotopies. The result is known as 𝖈𝖗𝖊𝖉𝖎's theorem. Crucially, 𝖈𝖗𝖊𝖉𝖎's theorem gives us a clean way of proving a certain quantity is a link invariant. All we have to do is show that the quantity is preserved under planar isotopy and the 3 𝖈𝖗𝖊𝖉𝖎 moves. For example, let's take another look at the linking number. I stated earlier without proof that the linking number of an oriented link doesn't change under any ambient isotopy. We can now prove this fact simply by showing that 𝖈𝖗𝖉𝖎 moves don't change the linking number.
Take 𝖈𝖗𝖉𝖎1. It creates or eliminates a crossing, but the overstrand and understrand of that crossing are part of the same link component. Thus, when we compute the linking number, that crossing is assigned the number 0, and its presence or absence has no effect on the sum.
So yeah, if you have 0,
Now
you
look
can
at
just cancel it,
𝖈𝖗𝖉𝖎2.
right?
It creates or eliminates 2 crossings. If the 2 strands involved are part of the same component, then both crossings get the number 0. Otherwise, one of the crossings gets the number 1, and the other gets -1. In either case, the sum of the numbers at the 2 crossings is 0, so the presence or absence of the crossings has no effect on the linking number. Finally, for 𝖈𝖗𝖉𝖎3, there are 3 oriented strands involved. Let's call them A, B, and C, and 3 crossings, the AB intersection, the BC intersection, and the AC intersection. After 𝖈𝖗𝖉𝖎3 is performed, we still have the same 3 intersections. And they're all assigned the same numbers as before because the rope orientations didn't change. Thus, the linking number didn't change. Hence, none of the 𝖈𝖗𝖉𝖎 moves changed the linking number. Since every ambient isotopy can be thought of as a sequence of planar isotopies interspersed with 𝖈𝖗𝖉𝖎 moves, the linking number doesn't change under any ambient isotopy.
Well, Sawyer, what do you
I
think?
guess.
Are we finally ready to prove why you can't untie your knot?
I sure hope so. All this talk about knots is making me want to tie you up in knots.
Sum them all
Bro,
up.
that was not in the script. We're cutting that out. Given a
Wait,
generic
what is it?
link,
Sorry.
Knots is making me want to tie you up in knots.
bro, that was not in the script. We're cutting that out.
No,
Given a
ayo.
generic link diagram, we want to associate a number with it, which is unchanged under ambient isotopies.
Just a couple,
To do that,
just couple
it needs to be
dudes.
unchanged under planar isotopies and the 3 𝖈𝖗𝖉𝖎 moves. We'll use this bracket notation to refer to the quantity associated with a diagram,
Oh my god.
which we'll call the bracket of the diagram.
Langle,
Remember
wrangle.
that if we want the bracket to be unchanged under planar isotopies, it's a good idea to define it solely in terms of the pattern of crossings of the diagram, similar to how the linking number was defined. However, the linking number was too simple. It only depended on the number of crossings and the sign of each crossing, and it didn't take into account more complicated information about how all the crossings were connected to each other. For our new invariant, we will want to somehow take this information into account.
Getting tied up with the
When you're
boys.
trying to define a complicated quantity,
Oh, so you
rather
like
than
my-
define it directly,
my
one
drawing?
idea is to define it indirectly using a recursive definition. You've probably seen recursive definitions before.
You can type LaTeX
They're
out. I
used when
love
it's
using it.
easier to define something in terms of smaller instances of itself rather than directly.
There we go.
The most famous example is the Fibonacci numbers, the sequence that starts 1, 1, and then each successive term is the sum of the 2 previous terms.
Fibonacci.
This
Yep.
definition is recursive because the nth Fibonacci number is not defined directly. Instead, it's defined in terms of smaller instances of itself, namely the previous 2 Fibonacci numbers. Keep in mind that the Fibonacci numbers are just one example out of many different possibilities. For instance, we could have started the sequence differently, then used the same rule to generate subsequent terms to get this completely different sequence. Or, instead of simply adding the previous 2 terms,
Actually-
we could multiply each of them by a different number and then add them. There are, of course, many other possibilities.
Are we gonna solve recurrence relations? Hold that thought, Aleph. I'm waiting.
Let's try
Um,
to use a
keep going.
recursive definition to define the bracket of a link. Instead of directly saying what the bracket is, we'll define it recursively in terms of smaller or simpler instances of itself. What's a simpler version of this link? Since we should only be caring about the pattern of crossings in the diagram, one idea for simplifying would be to reduce the number of crossings. So let's zoom in on one of the crossings. Since this is a generic link diagram, a crossing consists of two non-parallel strands, the overstrand and the understrand, intersecting at a single point. To eliminate this crossing without changing anything else about the larger diagram, we could do some link surgery and have the strands connect up like this instead, or like this.
Yes.
Zooming out, this means we could make two modified link diagrams that look entirely like the original one, except in one small region where a crossing was removed.
Okay, let's take a step back here because that was a lot to digest. We have a link diagram, which we want to recursively define an invariant for. To do so, we need to create simpler versions of the diagram. And since all we care about is the pattern of crossings, a simpler diagram would be one with fewer crossings. So, we focus in on one of the crossings and get rid of it. There are two sensible ways to do that, resulting in these two diagrams, which are considered simpler versions of the original. Now,
what is the bracket of a poop knot? What is the bracket of a poop knot?
here's where the recursive part comes in. Similar to how the Fibonacci numbers are defined, the bracket of the original link will be the sum of the brackets of the two simpler links.
We do need a simpler drawings of the poop.
Not quite. If we use this equation exactly, it turns out that we get a pretty useless invariant. For the sake of time, we won't go through those details.
Useless.
To get a more useful invariant, we can add more flexibility into the definition, like so. Instead of simply adding the two brackets together, we'll first multiply each by a different fixed number and then add. This is called a skein relation.
Note that this skein relation only involves a single crossing, and it should hold regardless of what the rest of the link is doing. Thus, for notational convenience, we can ignore whatever else is going on and just draw the changes happening to the one crossing. These partial diagrams should be interpreted as complete link diagrams, which are the same outside the region pictured.
Okay.
Now, we still need to determine what the numbers a and b should be. We have some freedom here, but they can't just be anything. We need to pick them in such a way that the bracket of the link is actually an invariant. More specifically, the bracket needs to be unchanged under the three 𝖈𝖐𝖈𝖐 moves. Let's look closely at 𝖈𝖐𝖈𝖐 2. These two links must have the same bracket because they differ only by a 𝖈𝖈𝖐𝖐 2 move. Again, assume that any part of the link not shown is the same across both diagrams. What happens when we apply our skein relation to get rid of the two crossings, rather than perform a 𝖈𝖈𝖐𝖐 move? Well, first tackling the top crossing, we get a times this picture, plus b times this picture. We have to be careful which picture gets the a and which gets the b. Looking back at the skein relation, we see that when the crossing is oriented so that the overstrand has positive slope, the a is attached to the picture in which the strands connect vertically, whereas the b is attached to the horizontally connected picture. If we rotate the entire link 90 degrees so that now the overstrand has negative slope, the a is attached to the horizontally connected picture and the b to the vertically connected picture. This is consistent with what we did.
Okay.
Now let's do the bottom crossing. This picture splits into two, with an a here and a b here. And similarly, this one splits with an a here and a b here.
I'm not gonna lie, I genuinely don't like this video. And it's not because I can't understand it. I think that's just my own bias, and I think I probably would want to skip this one. I'm genuinely getting upset by watching this. Because it's like, this doesn't feel like math. This feels like recreation in a way that makes me not feel like I'm interested in it. Does that make sense? I feel like I really don't want to say anything bad about it. But that's because I genuinely just don't like this subject. Oh no. I'm like actually getting upset. That's not what I want. That's not how we should be grading these. That's pretty biased. Oops.
At this point, we've gotten rid of both crossings, and we have a sum of 4 terms. We can simplify things a little using a...
And I don't blame them for like covering this subject. It's just like none of this seems very interesting to me. It's like covering like Shakespeare in a class of like I hate knots. There's a way to deliver this without making it sound like weird, because I saw how cool it can actually get, but this is like this is like the Ramstein theorem, the Ramstein theorem. Did you know that if you had a metal and you put another metal and you made it spoke German, then it makes a band? It's just like, okay, what does that mean? I don't know what you're talking about here. This is like a subject where I'm genuinely just like getting a little like, what is this telling me? Genuinely, what does this mean? and this is there's probably a lot of context that I covered back here, but I'm still like, isn't this obvious? Can't we just like untangle it? How does this tell me? Like, we haven't actually used any of the numbers yet either, because we're all still using this notation. We're using, okay, upward slope, downward slope. I thought you can add across the entire like knot and then find like a number, and if we can find zeros, then we can like solve them to be, I don't know, we can undo those steps. Or if they aren't zeros, then how does this add up, and then how does that identify it? I thought we were going to do something like that, but no, we're still using this stupid knot notation. I'm getting heated. I'm sorry. I don't think I should vote on this one. I will watch the rest of it. I'm just curious as to like the extent. It seems like just a couple guys like hanging out and making a fun video, but this doesn't seem fun to me. But I mean, so I'm also probably like on the end of my like wick, so this is probably just me being hangry and like watching this. So forgive me.
Your isotopy to smooth out the diagrams and combine like terms.
See, like, and then there's algebra now.
Now, the question is, what values of a and b would make this equation true?
I don't know.
Well, if these two terms canceled each other out, and a times b were 1, we'd have it. So let's substitute a inverse for b.
Why?
Now these two terms cancel, and after one more rearrangement, we get that the bracket of this link has to be negative a squared minus a to the minus 2 times the bracket of this link.
Why?
But the two links differ only by this one extra circle, which doesn't intersect the rest of the link.
How did you get
this
that?
Equation is basically telling us another rule that the bracket has to satisfy. Whenever you have a closed loop that doesn't intersect the rest of the link in any way, you can remove it as long as you multiply by a factor of negative a squared minus a to the minus 2. That handles 𝖈𝖗𝖊𝖉𝖎𝖎𝖙𝖘 2. To summarize, we have two skein relations so far.
I'm just curious as well. I want to
using
see
a
like
inverse for b,
what the
and this new one that tells you can remove a loop
consensus
and multiply
is.
by negative a squared minus a to the minus 2. We still have freedom in what a is.
Now, let's ensure the bracket is unchanged under the
Great
other
explanation.
𝖈𝖗𝖊𝖉𝖎𝖏𝑚
I'm glad someone
Take a
called
look at
that
our
out.
𝖈𝖗𝖊𝖉𝖏 situation, where we want to pass
that
a
was
strand over our
wild.
crossing. Using our first skein relation, we can remove the bottom crossing to get this equation. In this diagram, we can slide the strand simply using a planar isotopy. For this diagram, we already know the bracket is unchanged if we do 𝖈𝖗𝖈𝖐 moves, so we're allowed to slide the strand like this, doing two 𝖈𝖗𝖈𝖐 moves. Now we can recreate the crossing we destroyed, using the skein relation in reverse. The conclusion is that the bracket of the original link is the same as the bracket of the link once a type 3 𝖈𝖗𝖈𝖐 move has been applied, so we don't need any additional constraints. Type 3 𝖈𝖗𝖈𝖐 moves already are guaranteed to preserve the bracket.
Last but not least, we need to investigate 𝖈𝖗𝖈𝖐 1 moves. Take a little loop and use our skein relation to eliminate the crossing. In the right diagram, we can get rid of the extra loop by multiplying by negative a squared minus a to the minus 2. Now after straightening things out, we can simplify and combine like terms to get this. There are two ways to proceed from here. The first way assumes that the bracket, as we've already defined it, is invariant under type 1 𝖈𝖗𝖈𝖐 moves, so the left-hand side untwists, and minus a to the minus 3 has to be 1. Hence, a can be any of the three complex roots of negative 1, which are negative 1, e to the i⁴, and e to the negative i⁴.
We were allowed to have complex values now? What? Bullshit. Are you serious? I understand some of this can get into complex analysis, but like, how did that get... What the fuck? Okay, I think these comments of yours have value. The transition in the video where they stop talking about the linking number and start talking about bracket polynomial is a bit too quick. I don't understand what the fuck to talk about. The lack of the outline is really... Yeah, okay, so my big gripe is just this notation still doesn't make sense. I understand the Radmeisters, okay? We're basically moving it around, but I don't know what that looks like as an operation. They mentioned it, I guess. They're like, we have like a 0 and it goes to like another 0. Or we have a -1 and a +1 and then they combine together to make a 0. I'm like, what? Why? But now we're going into like algebra, and I don't even know how this algebra is actually operating on a real knot. And if this isn't a real knot, then why are we using real knots to describe this thing when we can't even show visuals of like the imaginary ones? Because we can have like the descriptions of like real knots that I've seen before where they phase through each other and they cancel each other out in weird ways. But in this case, I'm just genuinely like, what are you talking about? And now we have complex values? Me when I don't understand how to tie my shoes? Like, come on. But that's just me. Again, I just don't want to dog it for apparently something everyone else is getting that I'm too stupid to understand. but I don't know. It's not my cup of tea, and I knew it wasn't my cup of tea. So going into it, it's nice when it makes sense, but it's not nice when it doesn't make sense. So I'm just in the right. Like, if this is presented to me, I'm just like, where did you get that? And if they say because it said so, then I would get annoyed. But sure, when we get to have imaginary values now, why not?
This gives us a valid link invariant.
But we're going to focus on the second way, because it leads to a better invariant. We'll leave the troublesome factor of minus a to the minus 3 there for now, and do something to cancel it out at the very end. What do I mean by that exactly?
I don't know.
Suppose we take a big complicated picture of a link, and we use the two skein relations to calculate its bracket, systematically eliminating all crossings and the loops that form when those crossings are removed. By the end of the procedure, we'll end up with some expression in terms of a.
Sure.
This isn't an invariant yet, because if we had started with extra twists, we would have ended with extra factors of minus a to the minus 3, according to this equation. The sensible thing to do would be to count all the twists in the original link and multiply by minus a cubed for each of them to cancel out the minus a to the minus 3. Doing that would make it invariant. This almost works, except the crossings which came from a twist might not be so obviously distinguishable from the other crossings.
Why not?
For instance, we could do some 𝖈𝖗𝖊𝖉𝖎𝖙𝖘 2 and 3 moves here to bury this twist in the middle. Now this crossing is not obviously part of a twist, but it still should count for a factor of minus a cubed. So it seems that the resolution to all of our woes would be to look at every crossing in the original diagram and have it count for a factor of minus a cubed. Well, we don't have to look at every crossing, just the ones where the overstrand and understrand come from the same link component, since when they don't, that crossing couldn't have possibly come from a twist. The factors of minus a cubed we'll call the canceling factors, since they're meant to cancel the unwanted factors of minus a to the minus 3 generated by 𝖈𝖗𝖈𝖐 1 moves. There's one more slight issue to address, which is that if the twist was like this instead, we would have ended up with minus a cubed. So the canceling factor for this crossing should be minus a to the minus 3. There's an easy way to distinguish the two cases. Start by introducing an orientation on the link, like we did before.
That's what we should have been doing. What the fuck are we talking about? We haven't talked about any orientation with these stupid links at all other than under and over. That's how I understood knots to be, is that we give it an orientation, we see what direction they go in, and then stuff like that happens. This makes more sense to me than all this. Me getting mad. Hold on.
When calculating the linking number. If, when you rotate the overstrand counterclockwise to match the understrand, the orientations align, then the unwanted factor is minus a cubed, and the canceling factor is minus a to the minus 3. On the other hand, if the orientations don't align, it's the other way around.
Now we finally have a true link invariant. To compute it, you start by calculating the link's bracket polynomial, using Rule 1, which tells us how to eliminate crossings, Rule 2, which tells us how to vanquish loops, and Rule 3, which tells us how to neutralize twists. Once you're done calculating the bracket, go back to the original picture and figure out what canceling factors you need by looking at every crossing where the overstrand and understrand come from the same link component and determining whether you should multiply by minus a cubed or minus a to the minus 3. The resulting expression in terms of a, with canceling factors included, we'll call the x of the link. It's invariant under planar isotopies because both the bracket and the canceling factors only depend on the pattern of crossings.
Okay.
It's invariant under type 1 𝖈𝖗𝖈𝖐𝑒 moves, since although the bracket changes when a type 1 move is performed, the canceling factors are there to automatically neutralize that change. It's invariant under type 2 𝖈𝖗𝖈𝖐𝑒 moves because the bracket doesn't change, and the two canceling factors generated or removed by a type 2 move always cancel each other out. Lastly, it's invariant under type 3 𝖈𝖗𝖈𝖐𝑒 moves because the bracket doesn't change, and the canceling factors don't change either. Thus, the x of a link is invariant under all ambient isotopies, and it doesn't even matter what a is. Since a can be anything, conventionally it's just left as a variable. This means the invariant we have isn't a numeric invariant, but rather a polynomial invariant, so we call it the x polynomial.
Alright, time to finally do an example and see the x polynomial in action.
I can't.
Let's go back to the knot we saw at the very beginning of the video, called the trefoil, which we couldn't untangle. We'll compute the x of this knot by first computing the bracket polynomial using the skein relations for crossings, loops, and twists, then applying canceling factors at the end. Let's start by applying Rule 1 to the bottom crossing to get these two terms. For the left term, we'll use Rule 3 to remove the twists. We just need to check the orientation of the crossing, which in both cases brings out a factor of minus a cubed. Now let's look at the right term, and apply Rule 1 again on this crossing here. That gives us these two terms. And we're once again able to use Rule 3 as we untwist them into loops. Looking at the orientation, the left term contributes a factor of minus a cubed, and the right term includes minus a to the minus 3.
Okay.
From here, we'll factor out the loop. Then apply Rule 2 to get the entire polynomial in terms of a. This finally gives us the bracket polynomial of the trefoil, so we're almost done. We just need to multiply by the canceling factors, as per Rule 4, by going back to the original diagram and checking every crossing between strands from the same component, which is all of them since this is a knot. There are 3 crossings, and each contributes an extra minus a cubed, which gives us an extra minus a to the 9 factor on top of everything. And with that, we've got our link invariant. Let's go!
Bro, calm down.
Since the x polynomial of a link is invariant under ambient isotopy,
Why didn't we just do operations like this?
no matter how we manipulate the trefoil, if we were to recompute the x polynomial, we'd get the exact same thing. That's a rigorous proof you can't untangle it, no matter what, because the x polynomial of the unknot is minus a squared minus a to the minus 2, which is different. Our definition of the x polynomial is a little bit unconventional, but if you've done any knot theory before, you may have heard of the Jones polynomial, which is probably the most famous link invariant, and it's very closely related to our x polynomial. It was discovered by mathematician Von Jones in 1984, who later won the Fields Medal in 1990 for his work surrounding the discovery. To get from the x polynomial to the Jones polynomial, you first divide by minus a squared minus a to the minus 2, then multiply by a to the minus 6 times the linking number, then replace every a with t to the minus 4th to get a polynomial in t. These steps don't change the fact that the quantity is an invariant, since if you remember from earlier, the linking number is also an invariant. The result is the Jones polynomial of the link, denoted with a v. The x polynomial and the Jones polynomial are more or less interchangeable, so we'll stick to using the Jones polynomial since that's the more conventional invariant.
Bruh, okay, fine.
Here's another interesting application. There are actually two different versions of the trefoil, the right-handed trefoil and the left-handed. We computed the Jones polynomial of the left-handed version. If you did the same for the right-handed, you'd get this instead. These two polynomials are not the same, which means the right-handed and left-handed trefoil really are different. There's no way to transform one to look exactly like the other, even though they look nearly identical.
One important question is the question of whether or not the Jones polynomial can distinguish any two distinct knots. This is unfortunately not the case. For
Bruh.
instance, it's known that these two knots are distinct, but their Jones polynomials are equal. So, while the Jones polynomial is quite powerful, it's not the end-all for knot invariance.
What about distinguishing knots from the unknot? If a knot has a Jones polynomial that isn't 1, then that knot certainly isn't the unknot, since the unknot has Jones polynomial 1. But if the Jones polynomial is 1, it's possible that the knot is the unknot, and it's possible that it isn't. Thus far, no one has ever found a non-trivial knot that has Jones polynomial 1, but no one has proven that it doesn't exist. It's an open question in knot theory.
There's a lot more we could say about the Jones polynomial and other knot theory stuff in general.
Oh,
but
you
we'll save
see
that for another
Santa
time.
Barbara?
If you want to mess around with more knots and links in your own
Don't even get me started. That makes so much more sense now. I'm just
spare
kidding. I
time,
don't
there's
really
this
have
website
anything to say.
called knotful.io that lets you draw your own links and find their Jones polynomial and other link invariants. It's a really great resource if you're interested in the topic. And really, knot theory is super vast and kind of underrated, so I would highly recommend looking more into it if I don't have time.
As usual, we left some practice problems on screen, so if you're keen to try out the ideas from this video for
That
yourself,
looks like my shoes. My shoelaces. Yeah, they look like my shoelaces right there. Like, actually. Like, legit. Look at that. Like, my shoelaces. They're definitely one of these ones. Eventually. It's kind of like that. But, yeah. I can't say I enjoyed this one. I'm very rude about it. My shoes. I'll just say, like, it was... Are my shoes knots or unknots? I don't know. That's for you to figure out, and for me to figure out, honestly.
for yourself, you can go ahead and give those problems a shot. Other than that, just next time you find yourself with a collection of tangled up loops and you don't know how to untie it, just remember the Jones polynomial. You might be trying to do the impossible.
Mine's not impossible. I did great. You didn't even finish.
Bro.
I feel like if I met these guys, I genuinely would have a blast with them. But I did not understand anything. So they stole my shoes. I don't know. I'll still like them. I'll probably follow up. I'm just like, I just didn't understand it. I'm gonna give it a 3.14. I didn't like it. I really didn't. I feel so bad though, because I'm like, surely there's a way to make this make sense. But it's just, did I distract myself early on? Did I understand any of this a bit? Why were we talking about polynomials? How did those operations make sense? Could you convince me that they worked without just like plugging in the jargon and then just throwing it out of nowhere? Or felt like it was like that. Like the trajectory we were going at with like these numbers and these values, and then all of a sudden we were talking about A's. I didn't quite follow it. This was a fairly difficult video for me to enjoy or get into. I thought we were going into the subject of knot theory with the idea of canceling knots with the description of over and under knots. I mean, in the context of the video, it makes sense. It's like they were trying to find the link number, right? With the idea of canceling knots with the idea of the link number. How do you delete words like that? I don't know. Instead, we covered a lot of jargon and operations without where I felt there wasn't enough foundation to go into it. This felt like a how do you delete words like that? Don't click that. Okay. This felt like a student lecture rather than a tutorial, since there almost seemed like there was more context that they knew to cover, that perhaps others had as well. Unfortunately, I couldn't grasp my head around the use case, the use of the operations here, and even more unsatisfied with how the algebra was introduced, since I didn't understand why we were using A, or even how these I think I can use wrangle not notation was used, or what value it served. Is this convention? How can we have the imaginary values? Holy smokes! That reveal, where it's like, oh, we can have. I mean, I understand how to get that, but I'm like, are those on the table now? Like, what's the deal there?
A different fixed number and then add. This is called a skein relation.
A skein relation. Okay, cool. I just don't know what rules are possible, what rules aren't possible in some of this stuff. And clearly it didn't deliver to me very well at all. And I don't want to be rude about it, but genuinely I didn't understand any of it. How are we solving polynomials with all this stuff? What's the significance of the imaginary numbers? Like, is that actually something interesting? How come we didn't explore that more? What sig is the value of an imaginary? Because those are values I pi to the over 3. So yeah, those are complex values. What is the significance of a value of a complex A, like in a equaling 1 e to the I pi over 3. So defrac I pi over 3 comma e to the 2I pi. If only there was another creator with the name I pi. Minus I pi over 3. Does this type correctly? Does that type correctly? Looks like it does. That looks pretty big, but still. Is it defrac? I probably want to use frac. Why does pi equal 3? Shut up, Tyler. Not in the mood for the shenanigans. Why did we gloss that over when that was very interesting to cover? Since there weren't any complex values we had before. I don't know. I just genuinely didn't like it. And what's weird is I'm not even giving it like the worst grade. The worst grade is something where I just genuinely didn't even understand it. This one just pissed me off. And I still have to treat it nicely. That's the worst part. So it goes to show, like, even though like this was I don't know, it was just different. I didn't like how they delivered this. In this video, in the investigation, can you tell how two knots are the same or different? We covered the Wiedmeister, the Wiedmeister. We had the Jones polynomial, which is the big reveal at the end, and then you covered this from a book. However, we have more elaborate discussion as to why the three Wiedmeister moves are all we need, and so on. Get the hell out of here. I'll never respect knot theory unless someone can convince me of the goodwill of knot theory. Knot theory can be either very interesting, no, very simple, excuse me, I'm not saying it's interesting, to explain, or in this case, overly complicated without explanation. Since I was wondering why we're using these operations and wondering if there was an easier way to do it. Most even seemed obvious. No, I want to say, like, and let me bring the music back. I was even wondering why some of these operations weren't obvious to try. How are the Wiedmeister moves? I'm trying to pinpoint where I feel where things went off the rails. Good luck on your end. I'm fundamentally pissed off. I started pretty simple. Granted, it just jumped in and out of the stream a couple times. Well, okay. They started just fine. There's a link number. There's things going on. I thought we were gonna go with stuff like that, but instead we go this detour about. I understand the connectedness. If there's multiple strings, clearly there's got to be multiple knots. Or whatever the case is, right? Then we introduce the Ramenstein, the Wiedmeister, the stupid numbers, and it seems like it's the most obvious thing. And I'm wondering, why didn't we just do this in the first place? What does this operation actually do? And they explain it, but
oh, shut up.
Finally, 𝖈𝖗𝖊𝖉𝖎𝖙𝖘 3 involves a violation of the condition restricting crossings.
Yeah, they're explaining it with the notation, with the jargon of knot theory. They're not explaining what it literally does to the stupid knot. How are the Reidemysters used in a literal sense, as opposed? I didn't understand what it does to the knot by itself, in simple terms. Since we were talking about, it was talking about it in the notation, the operation. No sharp points or vertical strands, no parallel crossings. Crossings must involve exactly 2 strands. Duh, that's obviously what a stupid knot is. But why? If they're talking about these rules, then use the notation for it. You know, there's a ways to make the knots look like knots, right? There's a very specific way we're talking about knots, and it spends like a good stupid amount of time talking about, like, well, we can't have intersection points, we can't have 3 points intersecting at the same time. Well, no shit. Sorry. But like that is what a basic knot is. That's just what a knot is. Obviously, that's what all the knots are for the jargon of the video. Like, if you want multiple examples of these stupid knots, then we're gonna have to draw them out. Like that. Like this one. Only 2 of them are intersecting. Only 2 of them are intersecting. I can point that out. I can clearly see what the point is, right? That's what, without explaining too many words, you just say that you have things going over and under, and then you make things move around, okay? There's over and under, and then there's like a direction to it. Clearly there's some like stupid thing about like slopes and stuff. Why do the slopes matter? Doesn't it matter? Like, can't I just turn this thing like 90 degrees and it looks like the same thing? I don't know. Oh, what's this knot? I don't know. I don't care. Clearly this is a special kind of knot, and that's the thing. It's like they didn't explain. They over-explained, or didn't under-explain. I don't know. They didn't explain what the knots actually look like. In layman's terms, what does it actually do? Like over here, can't I just do an operation where I just flip the stupid thing? That's one of the Reidemysters knots operations. But it just made too much sense to explain it clearly. I didn't think I'd get this heated about this stupid math. Sorry, that's surprising. I didn't understand what it does in simple terms, since we're talking about how it confines to the rules of the knot. Also, it seemed the rules of the knot were also obvious. I can probably grab that sound clip and probably grab it. What's this knot? I don't know. I don't care. It's a stupid thing. Okay. This is the beauty of at least getting mad about stuff. It's like I can at least pinpoint this part versus the other economics one where it's just like, what the hell is going on? I don't even know if you're right or wrong. This I know for sure. Like, you could have explained it to me a bit better, because literal children can understand this stupid stuff. Look, I have graphics to show me that there's some of these stupid knots. Look, I can go over here. I can make a curve. I can make an actual knot. I can make the simplest one. Right? Preset. 7x6. What does this mean? I don't know, but it's possible to get one. What about the coil? That looks cool. This is completely irrelevant to most of these things, but that's a knot. What about there's a slinky. Oh my gosh, that's amazing. Woo woo. That's a knot, right? No, it's just a curve. But there's the other kind of knot that we're just covering, right? The basic of the basket. Oh my gosh. I don't know. I'm just getting mad at this point. Anyways, I want to wrap this up, and then I want to go get some food. I think I'm hungry. Also, obvious to the layman, but over-explained here that I felt even more why we didn't use more diagrams to get the basics down. Do we have a mod in chat? No. If Gauss isn't here, no, Gauss isn't here. It's just me. It's just me, baby. Is that how it's spelled? Layman? Close enough, yeah. I was even more confused why we use more diagrams to get the basics down. I feel I just feel so out of the loop. No pun intended. About this video that it upset me that we continued without, like, it made me question my basics of understanding about this stuff. About this video that upset me that we continued I knew enough of the basics beforehand to watch this video. Oh yeah, I feel like I'm even stupider having had a little bit of context going into this, and then now I'm even more confused. High school and undergraduate. Fuck you. Sorry. Anyways, any other last comments? Any last minute things I should probably say before, you know, I send a scathing review? UC Berkeley. Sorry, UC Santa Barbara. I'm from Southern California, so you know what? UC Santa Barbara. Now my reputation of Santa Barbara is now decreased. Okay. Let's look ahead. Let's look at who we're gonna raid. Okay. I want to wrap things up. I want to know who's like available. Vote. All right. 𝖈𝖗𝖉𝖎𝖙𝖘. I'm not gonna do that right now. We're gonna go ahead and raid someone. I'm taking you guys somewhere. Okay. Simplex is doing something. With kitties, please. We're the intro to Trig, or I can take you guys to one of my VTuber friends. Echo is just playing Persona 5 right now. Oriana's probably about to start stream right now. Let me see what Oriana's doing. And Simplex is in fact doing something. If you guys don't know Aura, she's a engineering VTuber. She covers a lot of really cool stuff, and she invents things almost weekly. Would you want to watch an engineer, or would you want to go to another math streamer so we can go and be friendly to our friends? We all friends with them. Yeah, she's the one that made me explode last time. It was very funny. So I may as well just go over and like bug her. And she just started streaming, so that means we have enough influence to like say hi. I'm gonna go say hi to her. I don't know. We don't have anybody else to follow up with the math streams, so that'll just be it for me. And then I think the next one we're gonna do is probably tomorrow. With Penn said he was gonna do it, so let's go ahead and bug them. All right. Thank you guys for watching. I hope you had a good day. I'll do my things more next time, and then we're gonna go bug people. All right. Have a good day. Thank you guys for watching, and then I'll see you next time, okay? And I have influence. I will just take you where I want. And I don't like knots anymore. Oh yeah, and then use the raid command. We're going to use if you're a subscriber, use the raid command. If you're not a subscriber, use the original one. So yeah. Thank you guys so much for watching, and I'll catch you guys next time, okay? Bye-bye, 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 bye-bye.